Have you ever wondered what's hiding at the bottom of the ocean? Not near the shore, not where the light still reaches, but miles down, in the pitch-black pressure, where no human could survive without a machine. The deep ocean is the strangest place on Earth. It's colder than ice, darker than night, and somehow full of life. Creatures that glow, fish with transparent heads, worms that live in boiling vents. Nothing down there should work, and yet it does. This video is made for slow minds and sleepy hours, a quiet science dive designed to help you relax, drift off, and maybe learn something along the way. If you enjoy science that helps you sleep, feel free to like this video and subscribe for more. And in the spirit of bedtime curiosity, let me know in the comments where you're listening from and what time it is there. I love seeing that quiet constellation of night owls light up the map. So take a breath, settle in, and let's go deeper than we've ever gone. The surface is restless. Waves rise and fall, chasing wind across miles of open sea. Light dances, bends, glimmers, fractured by ripples. Salt spray kisses the air. Boats drift, seabirds cry. The world above is wide, bright, and full of motion, but drop below the surface, and everything begins to change. It happens slowly at first, a dimming of color, a softening of sound. Blue deepens to indigo. Temperature drops, pressure grows, and sunlight, that constant companion, begins to retreat. The human eye can only see so far into water. Even the clearest ocean only allows light to travel about 200 meters. Beyond that, the brightness fades, and a new world begins. Oceanographers divide the sea into zones, layers based on light, temperature, and pressure. The topmost is called the epipelagic zone, also known as the sunlight zone. It's where life is busiest. Here, coral reefs bloom, phytoplankton perform photosynthesis, fish chase each other in darting bursts of silver, turtles surface to breathe, then vanish again. This is the part of the ocean we know, the visible, accessible shallows, where sunlight still has a voice, but we aren't staying there. Below 200 meters, sunlight thins to a blue whisper, colors vanish, red disappears first, swallowed by water, then orange, then yellow. By 500 meters, only a pale trace of blue remains. We have entered the mesopelagic zone, the twilight zone. The water here is colder, denser. Every 10 meters, pressure increases by 1 atmosphere. At 500 meters, it's 50 times the pressure of the surface, enough to crush unprotected lungs. Still, life continues. Here swim lanternfish, their bellies lined with soft glowing patches. Hatchetfish, razor-thin, mirror-skinned, reflecting the faintest trace of light to vanish in plain sight. Vampire squid drift with arms webbed, like cloaks, trailing bioluminescence like embers in the dark. These creatures are built for mystery, small, delicate, slow-moving. Many rise toward the surface at night to feed, then return to the deep by dawn. This migration, known as diel vertical migration, is the largest daily movement of biomass on the planet, and yet, we rarely see it. We descend further, past 1,000 meters, all light is gone, not dim, not faint, gone. This is the bathypelagic zone, the midnight zone. The world here is black, still, and brutally pressurized. The temperature hovers just above freezing. The pressure exceeds 100 atmospheres, the weight of a car on every square inch. Most submarines can't survive this deep without thick steel hulls, and yet, life does. Creatures here do not rely on eyes. Some have no pigmentation, others are translucent. Their defense is invisibility, their weapons are light. Bioluminescence rules this world. It is not rare here, it is ordinary. 90% of animals in the mid and deep ocean can produce light, but not light like the surface. This light is chemical, internal, organic. It pulses through jellyfish, like neon veins. It flickers from shrimp tails, bursts from startled squids, lures prey with tiny living lanterns. The anglerfish dangles a glowing orb in front of its face, a bait, lit from within, drawing the curious too close. Light is no longer something you see, it's something you become, and then deeper still, we cross into the abyssopelagic zone. The name means bottomless, though it isn't. It reaches down to 6,000 meters, a world of near absolute black. Few creatures dwell here. Those that do are slow, soft-bodied, metabolically efficient. Some survive for decades without ever surfacing. Others drift motionless, waiting for the fall of food, marine snow to arrive. Marine snow is not weather, it is decay, a constant slow rain of dead plankton, fecal pellets, body parts, mucus, and microbial fragments. What dies above, feeds the depths below. It drifts in silence, soft, constant, unseen by the surface. The seafloor begins to appear, a vast plain of fine sediment, scattered bones and silent ridges. You would expect it to be still, but the seafloor moves, not quickly, not loudly, but it shifts, it breathes, it tears open. Hydrothermal vents split the Earth's crust, gushing superheated water laced with metals and chemicals. At the base of these vents, life, not dependent on light, dependent on heat and chemistry. Bacteria feed on hydrogen sulfide, a gas toxic to surface life, and form the base of an entirely separate food web. Tube worms, clams, crabs, all clustered around the warmth, flourishing in boiling poison. This is chemosynthesis, the quiet cousin of photosynthesis. Life not from sun, but from stone. It is here, at the bottom of everything, that life shows us how flexible it truly is. It doesn't need warmth, it doesn't need sunlight, it needs time, it needs chemistry, it needs pressure. This isn't the ocean we know. It's a different Earth, one that operates without us, and it is vast. The average depth of the ocean is over 3,700 meters. The deepest trench, the Mariana Trench, plunges nearly 11,000 meters. That's deeper than Mount Everest is tall. In 1960, a manned submersible called the Trieste reached the bottom of the trench. It stayed for just 20 minutes. Since then, only a handful of people have returned. Fewer humans have visited the deepest ocean than have walked on the moon. And still, the deep remains, full of silence, full of pressure, full of motionless patience. The bones of whales rest here, entire skeletons scattered on the seafloor, becoming reefs of their own, known as whale falls. These oases provide food for decades. First sharks come, then scavengers, then bone-eating worms with no eyes, no mouths, just acid. Even in death, life continues. The ocean floor is not dead, it is just unfamiliar. Here, time stretches, evolution slows, and nothing is wasted. Gigantic isopods, relatives of pillbugs, crawl across the mud like ancient robots. Blind shrimp cluster around thermal vents, guided by heat sensors. Ghostly octopuses brood over eggs for years, motionless, until they hatch, and we still know almost none of them. Over 80% of the ocean remains unmapped, unobserved and unexplored. Every year, new species are discovered, new vents open, old ecosystems collapse, and rebuild. This is not a static world, it is alive, but in a language we have not yet learned to speak. The deep is not empty, it is saturated with pressure, memory, resilience, and rhythm. It is the planet's archive, a dark, breathing vault holding the story of Earth, not just as it is, but as it was. The tectonic plates that built our continent still drift beneath us. Volcanoes still rise from trenches in complete silence. Sediment still settles from above, carbon still sinks, and heat still pulses from the core. This place is untouched, not because it is empty, but because it is hard to reach, difficult to see, even harder to understand. But it's here, massive, enduring, and writing the oldest chapters of life. And as we move deeper into this world, we begin to realize that the ocean isn't hiding anything from us. It's simply waiting, waiting to be seen, waiting to be heard, waiting to remind us that mystery still exists. And ahead, Something stirs, not current, not weather, a faint flicker in the distance, a soft flash. It isn't sunlight, it's something else, something alive. We drift toward it. Let's keep going. Light is not supposed to exist down here. The sun is gone, completely, not dimmed, not faded, gone. We are now thousands of meters below the surface, suspended in a pressure greater than a skyscraper could withstand, surrounded by blackness so pure it feels almost solid. The silence is absolute, the cold, constant. There is no moon, no current, no weather, just stillness. And then, a pulse, soft, blue, unexpected. Another follows, then another, flickers in the dark like distant stars, only closer, moving. This light does not come from the sky, it comes from the creatures. Down here, life does not rely on light, it generates it. This is bioluminescence, nature's cold fire, chemical light made inside living cells, without flame, without heat. It is not rare, it is everywhere. In fact, it's more common in the deep ocean than sunlight is at the surface. 9 out of 10 species down here can produce their own glow. They blink, flash, fade, spark. It is not just decoration, it's communication, camouflage, hunting, mating, warning, deceit. To survive in a world without light, life had to become the light. The chemistry is simple. In principle, a molecule called luciferin reacts with oxygen in the presence of an enzyme called luciferase. The result is light, pure, cold, and usually blue or green colors that travel farthest through seawater. But the simplicity ends there. Every species glows differently. Some emit short bursts, staccato warnings to ward off predators. Others maintain a soft glow, like a lantern carried through fog. A few use elaborate flashes, coded signals to mates or rivals, readable only by their own kind. Some flash when disturbed, a defensive spark. Imagine a tiny shrimp, grabbed by a predator, releasing a burst of glowing chemicals into the water. Suddenly the hunter is glowing too, exposed in the dark, vulnerable. Others use bioluminescence to attract, like the anglerfish. Its glowing lure dangles from its forehead like a crooked finger, twitching gently in the dark. Smaller fish, drawn to the light, drift closer, until it's too late. Bioluminescence also helps creatures hide. Paradoxical, but true. Some fish glow on their bellies to match the faint light from above, becoming invisible to predators looking up. This is called counter-illumination. Light is camouflage. They vanish not by being darker, but by glowing just enough to blend in. A few even weaponize it. The deep-sea dragonfish carries bioluminescent spots near its mouth, allowing it to see its own reflection in a prey's eyes, like a sniper spotting glint from a scope. It can flash red light, rare in the ocean, invisible to most other creatures. It becomes a hunter in near-perfect stealth. And then there are jellyfish, some of the most beautiful organisms in the sea. They drift with pulsing grace, their gelatinous bodies trailing tendrils lined with cells called photophores. Each pulse triggers a cascade of light, glowing in rhythmic waves, blue, green, sometimes violet. In the dark, their bodies look like living galaxies. Others explode when attacked, not physically but visually. Bursts of light erupt from their bodies in sudden dazzling displays, like fireworks blooming in slow motion. Some creatures glow to mimic other creatures, some to confuse predators, some use light as a language, and some, we still don't know why they shine. Bioluminescence is one of the least understood phenomena in biology, not because it's rare, but because it's difficult to study. The pressure here would crush most equipment. Light-sensitive creatures vanish when bright instruments approach, and for every species we've studied, there are dozens more we've only glimpsed once or never at all. A tiny cone jelly, barely the size of a thumbprint, refracts light through its cilia, creating rainbow pulses. A siphonophore, hundreds of meters long, glows from tip to tip in a coordinated way. A cluster of ostracods, shrimp-like creatures, flash in perfect synchronicity to form luminous spirals, luring mates in the void. The deeper we go, the stranger the light becomes. Some creatures emit light through symbiosis. Bacteria live inside specialized organs and glow on behalf of the host. In return, they're given nutrients and protection. The flashlight fish, for example, uses glowing bacteria beneath its eyes like headlights. It can even shut off the glow by closing a flap of skin, like turning off a lamp. Others have evolved completely internal systems. No bacteria, just chemistry. It's efficient, precise, quiet. The colors too vary. Blue and green dominate. They travel farthest through seawater, but some organisms use red or infrared, visible only to specific species. It's like passing secret messages in the dark. We once thought deep sea life would be sparse, sluggish, dim, but this world glows, not with sunlight, but with invention. It's a kind of innovation that feels poetic. In the darkest places, life became light, and in that light, something else is revealed. Movement, fish, drifting with light, trailing from their fins, shrimp pulsing in Morse code, jellyfish, tumbling like falling lanterns, tiny crustaceans spinning spirals that fade in seconds. This world is not chaotic, it is orchestrated. Each flicker has purpose, each flash tells a story. We just haven't learned the language yet, and though the light seems magical, it's practical. Bioluminescence conserves energy. It requires no heat. It produces no sound. It alerts no current. Perfect for the physics of the deep, where energy is rare and stealth is survival. Even whales pass through this realm, slowly, silently. Their massive shapes cut through bioluminescent clouds, leaving trails that shimmer and fade. What we see as beauty is really information. Evolution shaped light into a toolkit. It lights the way forward, warns of danger, attracts life, and tells others where to go. It is not light as we know it. It is life, distilled into flicker, and still we've only seen the beginning. The deeper layers, the trenches, the Haddle Zone, may carry even more surprises. Species we've never named, signals we've never decoded. But for now, in this part of the ocean, the darkness is alive with meaning. It isn't empty, it's glowing. Ahead, something begins to rise from the seafloor, not a creature, a structure, the first signs of event, where heat, not light, gives birth to life. Let's move closer. The seafloor rises ahead like the edge of another world. It is not smooth, it is not silent, it breathes. What first appears as rock begins to stir with movement, not from creatures but from Earth itself. A fissure, thin and black, and steaming. Then another, then a column of smoke, not from fire but from water boiling within stone. This is a hydrothermal vent, one of the most unlikely, violent and miraculous places life has ever called home. Hydrothermal vents are underwater geysers. They erupt not with flame, but with scalding, mineral-rich water, often hundreds of degrees Celsius. So hot, it should kill. So deep, the pressure alone should flatten anything near it. But somehow, here, life begins. It starts in the dark, in the cracks of the ocean floor, where tectonic plates drift apart, leaving behind raw edges of Earth's crust. Cold seawater seeps into these cracks, pulled downward by gravity, pressure, and heat. It travels miles below the surface, deeper than light, deeper than most life, down into the mantle, where temperatures rise and the water changes. No longer ordinary, it reacts with rock. It gathers heat. It absorbs minerals, iron, sulfur, manganese, silica, methane. Then suddenly, it is forced back upward. The water returns to the ocean floor through narrow chimneys and fissures, released in violent jets of superheated liquid. These are hydrothermal vents, fountains of dark water rich with dissolved metals and gases, rising like smoke through the cold. And at the edge of that smoke, something moves. Worms, mussels, shrimp, crabs, an entire ecosystem gathered around fire in the deep. The water is too hot to touch. The surrounding ocean is near freezing. Yet life here does not simply survive, it thrives. Towering tube worms rise like pale candles, each over 6 feet tall. They have no mouths, no digestive systems. Inside, they host colonies of bacteria, millions of them, that feed on the chemicals from the vent. This process is called chemosynthesis. It is the deep sea's answer to photosynthesis. No sunlight, no chlorophyll, no green, just heat, hydrogen sulfide and bacteria turning chemical energy into food. These bacteria are the producers, the base of this strange food chain. Every creature near the vent depends on them. Crabs graze on bacterial mats. Mussels and clams filter the mineral-rich water. Shrimp cluster in swarms, feeding and breeding in the warmth. Instead of sun, they rely on stone. Instead of light, they depend on chemistry. This is one of the few ecosystems on Earth, not powered by the sun, and it is ancient. Hydrothermal vents may have existed for billions of years. Some scientists believe life itself may have started in a place like this, not on land, not in shallow water, but here in the dark, among minerals and heat and pressure. The vents themselves are short-lived by geological standards. Some last decades, others a few centuries before going dormant. But even after they go cold, the life remains. The surrounding rock cools slowly, the organisms migrate, and nearby a new vent begins to open. The cycle starts again. Chimneys of solidified minerals rise like towers from the sea floor. Black smokers, white smokers, shimmering spires coated in microbial layers. Each vent is unique. Each emits different minerals, different temperatures, and supports different species. The variety is staggering. Some vents are dominated by tube worms, others by clams, some by sulfur-eating snails with armored feet made of iron. There are shrimp with no eyes, only heat-sensing patches on their backs. Crabs with brush-like claws used to farm bacteria on their own bodies. Jellyfish that flash with bioluminescence above the vent fields. The density of life here is astonishing. In a zone that should be sterile, devoid of energy, thousands of species flourish, and we are only just beginning to understand them. Hydrothermal vents were first discovered in 1977 by accident. A team of scientists exploring the Galapagos Rift expected only rock. What they found instead was an entire ecosystem, thriving without sunlight, unlike anything they'd seen. It changed biology. It proved life could exist in places we never imagined, and in ways we never considered. It sparked new questions. Could similar systems exist elsewhere in the universe? On Europa, the icy moon of Jupiter, with its subsurface ocean and heat from tidal forces. On Enceladus, a moon of Saturn, where jets of vapor shoot into space from beneath its frozen shell. If life can exist here in toxic heat, total darkness and extreme pressure, maybe it can exist there too. Hydrothermal vents became more than science. They became possibility, but they are also fragile, delicate structures dependent on a balance of heat, chemistry and flow. Disrupt the balance, and the ecosystem collapses. As deep-sea mining grows, companies are exploring vent fields for valuable minerals, copper, zinc, rare earth elements, locked in the chimneys waiting to be extracted. But these aren't just rocks. They're homes, ecosystems, laboratories of life. Destroying them for short-term gain means losing species we've only just discovered, and others we haven't met yet. Many vents are now protected. International laws restrict mining in key areas, but enforcement is difficult, and the ocean is large. For now, the vents continue, each one unique, a fingerprint of the Earth's interior, each supporting life unlike anything above. When you look closely, even the minerals shine. Iron sulfide glitters like soot-covered gold. Manganese coats stones in metallic purple. Microbial mats ripple in layers, each a different shade of white, yellow or green, depending on the bacteria. It is not a colorful world, but it is vibrant. Everything here has adapted, not in defiance of heat, but because of it. Life found a way not to endure the extremes, but to build upon them. It is a reminder that Earth is not tame, that the unknown is not always elsewhere. Sometimes it's right beneath us, burning, churning and alive. And all of this, the vents, the chemistry, the bacteria, happens in complete silence. The ocean muffles it all. No explosion, no crackle, just heat pouring upward, quietly feeding life. And above it all, stillness. Whales pass occasionally, far above. Currents move around, not through. The rest of the ocean watches, unchanged, unmoved. This world is separate, and as we drift near the edge of a vent field, we can see the boundary, where life begins, and where it disappears again into the dark. Further on, the seafloor levels out, the light from the vents fades, and we begin to glide once more through the cold, high-pressure dark. But we are not alone. Something moves in the distance. Not vents, not fish, something larger, a slow, deliberate shape, a soft echo, the sound not of water, but of something ancient, a song. We're entering whale territory. Let's follow the sound. The ocean carries sound farther than any other place on Earth. Not light, not color, but sound, pure and unbroken, gliding across thousands of miles in the liquid dark. Here, in the deep, where sunlight fades and pressure builds, sound becomes the primary language, and no voice is more haunting, more graceful, more ancient than the voice of a whale. It starts low, a rumble, almost too deep to hear, felt more than heard, then rises, slowly, into a soft moan, then falls again, long and trembling. This is not noise, it is music. Whales sing. Not all whales, only certain species. The most famous is the humpback. Their songs are long, structured, and strangely beautiful, each one a pattern of moans, clicks, cries, and echoes that loop and evolve over time. Some last minutes, others stretch past the hour mark, and every male in a region will sing the same version, changing it gradually, together, like a drifting choir. But why? We don't know for sure. Maybe to attract mates, maybe to communicate, maybe something deeper, something older, a memory passed through sound. The songs change each season, notes shift, phrases evolve. It's not random, it's patterned, like language, like story, the longest continuous vocalizations of any animal on Earth. And they happen here, in the deep, where sight is useless, where current and silence are broken only by these slow, melodic calls. Other whales don't sing, but they do speak. Blue whales, the largest animals to ever live, use infrasound, sounds so low, we can't hear them with our ears, but we can detect them with instruments, or sometimes feel them in our chests. These signals travel across entire ocean basins, from the southern hemisphere to the North Pacific, from pole to pole. A single blue whale's call can echo for over 1,000 miles. Imagine sending your voice from California to Alaska, and someone hearing it, clearly hours later. Sperm whales, with their enormous block-shaped heads, speak in something even stranger. Clicks, fast, loud, dense. They click, in rhythmic bursts called codas, like sonar, like Morse code, like thought. Each clan, a group of related sperm whales, has its own dialect, its own rhythm, its own signature. They pass it on to their young. They recognize each other by it. They use it to bond, coordinate, navigate, even socialize. They live in matrilineal societies. Grandmothers teach the young. Mothers protect the pod. Males leave when grown and wander alone. Some scientists believe these vocalizations are the closest thing we've found to cultural language in non-humans. It's not just instinct, it's learned, it's shared. Whale communication doesn't stop at song or click. It includes silence, proximity, touch, movement, a fin sweep, a body roll, a synchronized dive, messages sent through action, not just sound. In some species, mothers whisper to calves, literally. Gray whale mothers have been observed lowering their call volume when close to their young, likely to avoid attracting predators, or simply to soothe. A lullaby. Underwater, we're still deciphering what it all means. Marine biologists have recorded thousands of hours of whale song, coda, click, and call, and we're only beginning to understand the syntax. The same way linguists once decoded human languages, we are now trying to decode the deep. In 2020, a project called TETI, the Cetacean Translation Initiative, launched to do just that, using machine learning, pattern recognition, and massive databases of sperm whale coders. The goal is simple: to translate, to listen, because if these sounds carry structure, and if that structure carries meaning, then maybe we are not the only species on Earth with language. Maybe we're just the loudest, and perhaps the least fluent in listening. Whales have been singing for millions of years, long before humans had language, before we stood upright, before we even existed. Their songs predate cities, predate history. They echo through water, like time itself, slow, mournful, unhurried. In their world, sound is memory, each pulse and pattern, a fragment of identity, a connection across generations, a way to find each other in the dark. And sometimes, in that darkness, other sounds appear. The L stone, a name given to a sound recorded in 1991, a deep, rhythmic thump, detected over an array of hydrophones in the Pacific. Never explained, never repeated, only heard once. The bloop, a powerful ultra-low frequency sound, detected in 1997, southwest of South America, louder than a blue whale, so loud it was picked up by sensors thousands of kilometers apart. For years it was thought to be biological, too structured to be tectonic, too strong to be artificial. Some believed it was the call of an unknown giant creature, something living in the farthest reaches of the ocean. Eventually, it was attributed to icequake activity, a shift in underwater glaciers. But still the ocean is full of such sounds, strange call signals that rise and fall, bounce and echo, with no clear origin. The deep is not silent, it is only waiting for us to learn how to listen. For whales, this is daily life. They sleep vertically, motionless in small groups, slowly rising and falling with each breath. They travel in pods, they raise their young, they mourn their dead. In 2018, an orca named Telequa made headlines when she carried her deceased calf for 17 days, nearly 1,000 miles, refusing to let go. She lifted it to the surface again and again. Was it grief, memory, emotion? Hard to prove, impossible to deny. Whales remember. They travel ancient routes across oceans, from polar feeding grounds to tropical birthing waters, thousands of kilometers, navigated by instinct, passed down through generations, possibly guided by magnetic fields, underwater landmarks, even the echo of seafloor ridges. And always, sound, the constant companion. Even in death, whales leave behind echoes. Whale falls, their bones settling on the seafloor become ecosystems. Dozens of species survive on the remains. A final gift. The cycle continues, and still the living sing. Their songs bounce off canyon walls. They pass through thermoclines and cold sea. They ride the deep sound channel, a layer of water, where sound travels the farthest, with the least loss. It's called the SOFAR channel, short for sound fixing and ranging. Whales may use it to send calls across entire oceans, a natural highway for song. And perhaps, just perhaps, some part of those echoes remains, swirling in the water, bouncing still. A message sent years ago, still on its way. In this realm, nothing is wasted. Even sound keeps moving. So as we drift through this world of echoes, we remember, life does not always shout to be heard. Sometimes it sings slowly, deliberately, for those who are willing to wait and listen. Ahead, the ocean begins to narrow. The seafloor lifts gently, currents twist and tug. Something ancient and slow emerges from the sediment, the remains of a wreck, a story long submerged. Let's move closer. The seafloor rises again, gently. Dark sand gives way to something harder, unnatural shapes. Not stone, not coral, steel, twisted, rusted, broken, but unmistakably human. A shipwreck. The ocean floor is not empty, it is full of stories. Some are fossils, millions of years old. Some are volcanic ridges and fault lines, and some, like this, are reminders of what we lost. Ships do not float forever. Storms strike, icebergs tear, war, error, time, gravity always wins. When they go down, they sink slowly at first. Bubbles rise, lights flicker, steel groans against pressure it was never meant to bear. And then, silence. What was once filled with light and voices becomes still. What once defied the ocean becomes part of it. Wrecks settle into the seafloor like bones into soil, and the ocean, with time, makes them beautiful again. This is not decay, it's transformation. In the deep, where oxygen is scarce and light does not reach, corrosion moves differently. Steel rusts slower, wood decays less. A sunken ship becomes a canvas. For time, for chemistry, for life. The Titanic rests here, 2.5 miles beneath the Atlantic. Sunk in 1912, it now sleeps in silence, its bow and stern broken apart, separated by a debris field that stretches like a trail of memory. Its iron hull, once pristine, is now pitted and softened by rust-eating bacteria. These microbes consume the metal, leaving behind formations called rusticles, icicle-shaped drips of iron oxide that hang like stalactites from beams and railings. They are not decoration, they are the slow dismantling of human ambition, and yet, they are also strangely beautiful. Even in decay, something new begins. Shipwrecks become reefs, structures for coral to cling to, shelter for fish, octopuses, crustaceans. Some attract entire ecosystems, predators and prey orbiting a skeleton of steel. And not all wrecks are ancient. Oil tankers, submarines, cargo vessels, thousands have been lost across history. Each one tells a different story, some intentional, some mysterious. In the South China Sea, the remains of World War II vessels still lie untouched. In the Black Sea, ships over 1,000 years old remain remarkably preserved, protected by anoxic conditions that slow decay. In the Gulf of Mexico, hurricane-damaged rigs lie beside 19th-century schooners, side by side, century and steel. Each wreck becomes a snapshot, frozen in place, locked beneath pressure and time, and each changes the environment around it. Metal structures disrupt currents. They create eddies, pockets of stillness. Sediment gathers differently. Biodiversity increases. Even man-made pollution becomes part of the cycle. Paint chips, oil residue, broken cables. The sea does not clean them away. It surrounds them, integrates them. Some wrecks are cleaned and placed intentionally, artificial reefs, to support marine life. Others are lost by accident or tragedy, but all are claimed. The deep doesn't care how something arrives, only that it's here now. Divers speak of a strange quiet when approaching wrecks, a silence deeper than usual, as if the sea holds its breath. There's weight to these places, not just physically, emotionally. They are remnants of effort, of ambition, of movement now gone still. But the ocean remembers in its own way. It weathers what it cannot keep, it hides what it cannot fix, and it adorns what it cannot erase. Shipwrecks become more than metal, they become part of the ocean's architecture, its history, its strange cathedral. Fish swim through windows, anemones cling to rivets, crabs scuttle across control panels. Sometimes everything is covered in a thick layer of silt, like dust in an abandoned room. And then, something moves. A flash of color, a fin, a slow swirl of disturbed sediment. Life always returns. Even human artifacts become habitats. Dishes, radios, helmets, tools. Octopuses nest inside teacups. Eels coil around wiring. Shrimp hide in boots. Nature doesn't waste anything. A ship is not just wreckage, it's surface area, structure, shelter. Even materials we once considered harmful, plastics, polymers, paint, can host microbial life. Bacteria form biofilms, tiny animals attach, and the longer it stays, the more alive it becomes. Some wrecks have vanished into biology entirely. The original form, unrecognizable beneath coral and colony. Others remain skeletal, hollow, and ghostly, but no less meaningful. And yet, shipwrecks aren't just physical, they're emotional. They carry stories, grief, memory, the people who built them, the voyages they carried, the storms they met. Some went down in war, some in peace, some in silence. All now rest in equal stillness. We study them with sonar, with submersibles, with deep-sea ROVs. We map them, measure them, model them, but always they feel like reminders of how temporary we are. And yet, in that transience, something profound. Our creations don't last forever, but for a while, they matter. They move through the world, they carry us, and when they're gone, They change the world again. The ocean doesn't erase them, it reshapes them. Some wrecks have become pilgrimage sites for researchers, divers, historians. Others remain unknown, logged only as dots on sonar, marked by nothing above. And some are found by accident. A sonar scan, a curious blip, a shadow on the seafloor, followed by footage, steel, silence, story. The ocean holds these memories without judgment. It is not sentimental, it is not cruel, it is simply vast. And in that vastness, there is room for memory. As we drift past this wreck, whatever ship it once was, we see the layers forming. A layer of iron, a layer of coral, a layer of sediment, a layer of life, one on top of the other, like pages in a book we've only just begun to read. A little further, and it disappears into the silt, its outline blurred, its presence absorbed, but its story, at least a fragment of it, remains, written now in barnacles and rust. And ahead, a change. The water begins to rise gently, temperature shifts, a slope of rock appears, not metal, not shipwreck, but earth itself. We are approaching the edge of a trench, and just beyond, the deepest places we've ever dared to look. Let's keep going. The seafloor changes. The flat, sedimented bottom begins to slope downward, slowly at first, then sharply, impossibly, into a vast black cut in the earth, a trench, a scar of unimaginable scale. We are now entering the Hedonol zone, named after Hades, the ancient Greek underworld. It begins around 6,000 meters deep and extends to the very bottom of the ocean. Only a handful of places on the planet reach this deep, and yet they exist. Long, narrow, winding depressions, often where tectonic plates meet, colliding, subducting, warping the crust. These are not valleys. They are deeper than valleys, deeper than mountains are tall, deeper than light has ever reached. The Mariana Trench, the Tonga Trench, the Kermadec, the Philippine, the Japan, names given to places where the earth bends in on itself. Here in the deepest known part of the sea, Challenger Deep, the ocean floor lies nearly 11,000 meters below the surface. If you dropped Mount Everest into this trench, its peak would still be submerged by more than a mile, and down here, the rules bend further. Pressure is the defining feature. Every 10 meters of depth adds another atmosphere of pressure. At 11,000 meters, that's over 1,100 atmospheres, more than 16,000 pounds per square inch. It is the equivalent of balancing 50 jumbo jets on a single human body. No unprotected human, no conventional submersible, no ordinary equipment survives long under that force. Steel buckles, glass shatters, fluids compress. The body, if unprotected, is crushed. And yet, something stirs in the dark. A slow flicker, a ripple in sediment, a creature, moving. Life is here, not just bacteria, not just microbes, complex organisms. In 2012, filmmaker James Cameron descended solo to Challenger Deep, a 7-hour dive, in a custom-built submersible. At the bottom, he found a quiet, desolate plain of sediment, but even there, signs of movement. Small shrimp-like amphipods, transparent, fragile, and yet alive. Later expeditions would find more. Snailfish, translucent, jelly-bodied vertebrates, capable of living at over 8,000 meters. Their bones are minimal, their muscles loose, their bodies adapted to pressure, with chemistry we still barely understand. They do not resist the pressure, they exist within it. Their cells contain compounds like TMAO, trimethylamine N-oxide, which helps stabilize proteins under extreme pressure. The same compound gives fish their ocean smell, but here it allows them to function where almost nothing else can. Even their enzymes, the tiny biological machines that drive life, are different, designed for a world where nothing is ever still, warm or bright. Pressure alters everything. It changes how water behaves. It changes how molecules interact. It changes the very shape of biology, and yet, life persists. Sediment cores taken from trench floors reveal dense microbial communities, thriving in the cold, digesting organic matter that drifts down from above, some of it freshly dead, some of it ancient. The ocean is not quick to let go. Even plastic has been found down here. A bag, a bottle, bits of microplastic embedded in the silt. Proof that even our waste can reach the furthest, quietest corners of the earth. And with it, come questions. If our trash is here, what else is? The Hedalol zone is still largely uncharted. Its pressure makes exploration difficult. ROVs, remotely operated vehicles, must be specially reinforced. Data is slow to collect. Visibility is low. Each expedition is costly, rare and short. But each time we return, we find more. Tiny crustaceans, flatworms, polychaete, creatures we cannot name because we've never seen them before. They are not fast. They are not large. But they are alive, breathing, metabolizing, adapting. And they live in places colder than ice, darker than night, under pressure that would pulverize steel. They challenge every assumption we once held about the limits of life. We used to believe deep meant dead. We now know deep means different. These trenches are not barren scars, they are repositories of sediment, of nutrients, of memory. Dead organisms drift downward for weeks, sometimes months. They fall like snow, marine snow, until they settle in the trench. Bones accumulate, shells, organic debris. Over time, these layers become archives, geological records of plankton blooms, algal shifts, even atmospheric changes. By analyzing the isotopes in sediment layers, scientists can reconstruct parts of Earth's past climate, year by year, layer by layer. The trench holds secrets, yes, but it also holds records. In these still valleys, time moves differently, slower, denser, and not just for life, for the planet itself. Tectonic activity here is relentless. One plate pushed beneath another, the crust folds, earthquakes rumble, sometimes imperceptible, sometimes massive. The 2004 Indian Ocean earthquake, which caused a devastating tsunami, began in a trench, 30 kilometers below the seafloor. The energy released was immense, shifting the Earth's mass enough to shorten the length of a day by microseconds. These places are quiet, but they are powerful. They move continents, shape coastlines, store carbon, hide heat. Some scientists believe that trenches may help regulate the planet's climate. Organic carbon, dead matter, from surface life, sinks into the Hedal depths, and is slowly buried, locked away, sequestered. If not for the deep sea, Earth's carbon balance might tip, climate might spiral, life, as we know it, might shift. The deep holds more than mystery, it holds equilibrium, and yet, we are only visitors here. Our machines hum, our senses scan, but the trench remains vast, indifferent, almost unknowable. There are places no one has ever seen, not even by camera, and in those places, life might be writing new rules, new shapes, new chemistries, new forms, not dramatic, not monstrous, but elegant, efficient, undiscovered. We often imagine the unknown as loud, aliens, cities, ruins, but maybe the most alien thing is silence, slow life, unhurried adaptation, creatures that never rise to the surface, that never feel the sun, that never need to. They do not envy the surface, they do not know it exists. Their world is whole, complete, enclosed by pressure, shadow and gravity, and somehow perfectly enough. As we drift along the trench wall, something glows softly in the distance, a pulse, a shape, a ripple in time, not another vent, not another fish, but a shimmer, almost reflective, the edge of a boundary, where life ends, and rock begins again. Let's follow it. The ocean has a shape, not just a surface, not just waves or tides, but a landscape, a world of ridges, valleys, plains, volcanoes, and trenches. It rises, it falls, it fractures, it tells a story in stone, one that few have seen. Because while we live on a planet covered mostly in water, we have barely mapped what lies beneath it. Over 70% of Earth is ocean, and yet more than 80% of the seafloor remains unmapped, unexplored, and unseen. We know more about the surface of Mars than we do about the floor of our own oceans. And still, the shape of the ocean floor influences everything above it. Currents, storms, climates, life. Continents shift in response to what happens beneath the sea. The ridges pull them, the trenches swallow them, the vents heat them. The ocean is not just a surface, it is a structure, and for centuries it remained invisible. Early maps of the sea were filled with guesses, lines and estimates, imagined plateaus, fictional islands, warnings of monsters and whirlpools. We knew where ships traveled, we knew the depths of harbors, but the vast middle, a mystery. It wasn't until the 19th century that systematic ocean depth measurements began. Using lead lines, sailors would drop a weighted rope overboard, wait for it to hit bottom, then measure how much line had unspooled. It was slow, manual, and almost useless for anything deeper than a few hundred meters. Then came sonar. World War I introduced a new method, sound navigation and ranging. Instead of dropping a line, scientists sent a pulse of sound downward. The sound wave would bounce off the seafloor and return. By measuring the time it took to return, they could calculate depth. The ocean floor began to take shape. What they found shocked them. It wasn't flat, it was mountainous, broken, woven with ridges and trenches. The Atlantic had a spine, the mid-Atlantic ridge, thousands of kilometers long, running from Iceland to near Antarctica. Trenches like the Mariana dropped farther than any land depression. Volcanoes taller than Everest sat silently beneath the waves. This discovery helped to launch the theory of plate tectonics. The seafloor was not static, it moved. New crust formed at the ridges. Old crust was pushed into trenches. Continents drifted atop these moving slabs of rock, driven by heat and gravity deep below. The ocean floor was no longer just wet dirt. It was the engine of Earth, and we wanted to see more. Modern bathymetry, the science of measuring seafloor topography, uses multi-beam sonar systems, mounted on ships. These systems send out fans of sound in wide arcs, measuring depth across a swath of seafloor as the ship moves. Each ping maps thousands of points. Each line reveals structure. With enough passes, the ocean floor becomes a 3D image, textured, layered, alive. But there's a catch. It's slow. A single ship can only map a narrow band at a time. Even working non-stop, it would take centuries to chart the entire seafloor. So we supplement sonar with satellite data. Satellites can't see the bottom directly, but they can measure the sea surface with incredible precision. Here's how it works. The ocean isn't flat. Its surface bulges slightly over underwater mountains and dips slightly over trenches, pulled by the gravity of the seafloor beneath. By measuring these tiny variations in sea surface height, we can infer the presence of features below. It's indirect, less detailed than sonar, but it covers the globe. In 2014, the satellite JASON-1 helped produce a map of global seafloor gravity, revealing thousands of previously unknown seamounts. But to see the fine details, the contours, the cracks, the texture, we still need ships. As of now, less than a quarter of the ocean floor has been mapped in high resolution. The rest remains shadows and guesses. Enter Seabed 2030, a global initiative launched to change that. The goal is simple, to map 100% of the ocean floor in detail by the year. It's a massive challenge, but nations, institutions, and research vessels around the world have joined forces, sharing data, standardizing formats, deploying technology. Autonomous underwater vehicles, AOVs, now roam the seafloor without human pilot. They carry sonar, sensors, and cameras, mapping the world below quietly, efficiently, often while we sleep. Some dive deeper than any submersible before them, others hover just above the sediment, capturing details no satellite could ever see. In 2019, an AOV discovered over 14,000 previously unknown undersea volcanoes in the South Pacific. They are everywhere, invisible mountains shaping currents, scattering nutrients, attracting life. Each mapped region adds to a global blueprint, not just of where the ocean is, but what it is. Mapping the seafloor reveals more than depth. It reveals fault lines, where earthquakes begin. It shows cold seeps where methane escapes the crust. It uncovers coral mounds, sunken wrecks, deep canyons, fossilized riverbed. In 2018, researchers found a massive coral reef off the coast of Australia, taller than the Empire State Building, that no one had seen before. Why? Because no one had looked. Mapping also helps us understand how the ocean interacts with climate. Seafloor topography affects how water moves, how heat is distributed, how carbon is stored, how deep currents circulate. A narrow ridge can block a current, a trench can trap sediment, a slope can guide cold water from the poles to the equator. The deep sea is the engine of global ocean circulation, the thermohaline conveyor belt. And to understand it, we need to know the shape of the parts. Without a map, we're guessing. With it, we're listening. And as we map, we find surprises, cracks that weren't there before, heat signatures where there should be cold, pillars of methane, movements of sediment. The Earth is not still, and neither is the ocean floor. Mapping the seafloor also reveals something more abstract, the scale of what we don't know. For every trench mapped, another remains hidden. For every vent studied, another steams alone in the dark. For every ridge discovered, another quietly shapes the current. The deep ocean is not a void, it is a landscape. It is sculpted, it is active, and by mapping it, we are slowly sketching the true face of our planet. Because the Earth isn't just land, it isn't just continents and coastlines, it is vast, submerged, and shaped by unseen forces far below. Mapping it is not just about navigation, it's about understanding where we come from, and how the planet breathes. We're building a blueprint of something ancient, something hidden, something alive. And even now, with all our tools, our satellites, our ships, our sonars, we've only traced the edge. Ahead, the seafloor begins to rise again, not into land, but into something warmer. The edge of a ridge, a spine of volcanic rock, with a strange heat pulsing beneath it. Let's follow the current. The ocean moves, not just on the surface, where waves dance in the wind, but deep below, where no breeze reaches. There are rivers here, invisible, immense, unstoppable, not made of fresh water, not bounded by banks, but moving just as surely with volume, force, and destination. They thread through the sea like veins, carrying warmth and salt, life and energy. They are ocean currents. To understand the Earth, you must understand these currents, because they are not just water, they are the planet's circulatory system. They begin with imbalance. The sun heats the Earth unevenly. The equator receives more energy than the poles. Warm water pools in the tropics. Cold water waits near the Arctic and Antarctic. But the ocean doesn't like imbalance, so it begins to move. At the surface, winds push water westward and poleward, curling with the planet's rotation. This is the Coriolis effect, a twist in everything that flows. Gyres form, large rotating systems of currents, in each major ocean basin. In the North Atlantic, it's the Gulf Stream. In the North Pacific, the Kuroshio. In the Southern Hemisphere, they rotate in reverse. These surface currents are fast. Some, like the Gulf Stream, move with speeds up to 2 meters per second. They carry warm water from the Caribbean toward Europe, softening the climate, feeding storms, sculpting weather. But surface currents are only part of the picture. Beneath them, deeper, slower rivers wind through the dark, driven not by wind, but by density, by differences in temperature and salt. This is thermohaline circulation. Thermo for heat, haline for salt. Where water gets colder, it becomes heavier. Where it gets saltier, often due to ice formation, it also grows denser. In the far North Atlantic, surface water cools, becomes saltier, and sinks. This sinking pulls more water toward it, creating a slow cascade, a plunging waterfall of cold, dense water that begins to spread southward, along the ocean bottom. It slips beneath the warmer layers. It hugs the seafloor, creeping toward the equator, then onward to the Southern Ocean, and eventually, around the world. This is the global conveyor belt, a looping system of deep, ocean currents, that moves water and heat across every major ocean basin. It takes centuries for a single parcel of water to complete the journey, from the surface near Greenland, to the bottom of the Atlantic, to the Pacific, and back again. But it never stops. It's why the deep sea isn't perfectly still. It's why nutrients get recycled, why carbon gets stored, why heat is redistributed. These deep currents mix the ocean, not just vertically, but globally, where they rise again, usually in the Southern Ocean or the Pacific. They bring nutrients from the deep: iron, nitrogen, phosphorus, the building blocks of life. These upwellings feed plankton blooms. Plankton feed fish. Fish feed the world. Without currents, the ocean would become a layered, stagnant soup. Stratified, starved, dead zones would expand, but with them, life continues. Currents also carry oxygen. As water sinks at the poles, it drags down surface oxygen, delivering it to the deepest trenches. That's why even the abyss breathes. In some places, these currents hit underwater mountains, ridges, or continental slope. The collision stirs the water, creating turbulence, tiny whirlpools that mix layers and move energy. It's one reason the ocean floor matters so much. Its shape determines how water moves. A trench can trap cold water, a ridge can deflect it, a slope can accelerate or stall it. Everything is connected, and the currents don't just shape life, they shape time. The Atlantic Meridional Overturning Circulation, AMOC, is one branch of the global conveyor. If it weakens or stops, climate shifts. Europe cools, rain belts move, monsoons weaken, sea levels rise along the US coast, and it can happen fast. Evidence from ice cores and ocean sediments shows that in Earth's past, AMOC has collapsed abruptly, within decades, not in slow motion, but in leaps. And today, there are signs of stress. Melting ice from Greenland adds fresh water to the North Atlantic, lowering salinity and disrupting sinking. Warmer global temperatures change evaporation and wind patterns. The conveyor begins to slow. If it halts, weather systems will stagger, fisheries will crash, tropical storms will wander into new regions, all from currents, unseen, unheard, but vital. Even the El Niño phenomenon, the irregular warming of surface waters in the Pacific, is tied to currents. It reshapes weather across continents. Floods here, droughts there, because the sea moved differently. But currents are not just physical, they carry meaning. Stories of ancient voyagers, Polynesians, Vikings, Arabs, they learned to read the ocean, not just waves and stars, but the hidden flow beneath the surface. A change in temperature, a drift of debris, a slight shift in salinity. Currents shaped where they sailed, where civilizations rose, where trade formed. Even marine life uses them. Eels spawn in the Sargasso Sea, their larvae riding currents back to Europe. Sea turtles hatch on beaches, vanish into gyres, then return years later. Salmon sense magnetic signatures shaped by ocean flows. Currents are not just rivers, they are highways, memories, tethers between past and future, and yet, we are only just learning to track them in detail. Cargo floats, small, drifting instruments, now pepper the world's oceans. They sink, they rise, they drift, measuring temperature, salinity and current velocity, thousands of them, creating a 3D, moving map of ocean conditions in real time. Gliders, satellites, buoys, moored sensors, all part of a growing network to monitor the sea's pulse. Because if we want to understand climate, we must understand motion. Still water is rare, everything flows. Even below the thermocline, that invisible line, where warm surface waters give way to cold depths, motion continues, slow, steady, relentless. Heat doesn't stay where it began, energy doesn't fade, it moves. And when you dive deep enough you feel it. Even in the silence, the cold, the pressure, there is movement, a brushing current, a subtle pull, like breath in the chest of the ocean. Sometimes, it feels like you're floating in place, but the water around you is on a journey, one that started before you were born, and may not finish in your lifetime. The ocean remembers. A current today might be carrying warmth from the 1990s, or carbon from the Industrial Revolution, or radioactive traces from distant tests. It moves everything: life, death, history. And just ahead, a shift in color, a gradient in the water, something warmer, lighter, changing, an eddy, a spinning loop of current breaking free, a spiral within the sea. Let's enter it. There are no straight lines in the sea, no fixed paths, no unmoving waters. Everything shifts, everything spirals. Currents that once seemed steady now begin to bend, twist, fold back into themselves, until the ocean becomes a canvas of slow-motion chaos. These spirals, some the size of cities, some as large as countries, are called eddies. They are the weather systems of the sea. When two water masses of different temperatures or salinities meet, a current can break free from its main flow, spinning off in a circular motion, like smoke curling from a flame. Some eddies spin clockwise, some counterclockwise, some rise from warm water, some form from cold. Each one is different, each one alive, and they are everywhere. Satellite imagery reveals them in brilliant color. Great rotating disks of thermal variation, blue cores ringed in red, spirals of cold water pushing upward from the deep, or warm water sinking slowly as it spins. In the North Atlantic, warm core rings peel off from the Gulf Stream, spinning into the cooler surrounding sea. These eddies can last for months, even years, drifting, rotating, slowly decaying. They don't just swirl water, they carry heat, nutrients, salt, life. A single large eddy can transport the equivalent of 1,000 rivers worth of water, quietly, steadily, invisibly to the human eye. And within them, strange things happen. Nutrients trapped in an eddy's center can trigger plankton blooms, feeding fish, whales, entire ecosystems. Larvae ride eddies to new shores, species are spread, populations shift. They're not just movement, they're delivery systems, but they're also unpredictable. Oceanographers used to model the ocean as orderly, a series of layered flows, predictable and linear. Eddies shattered that idea. They bring turbulence into the picture, non-linearity, a kind of beautiful organized chaos. And the deeper we look, the more chaos we find. Beneath the surface gyres, the large circular systems that dominate each ocean basin, there are sub-gyres, micro-eddies, filament flow, a fractal system of nested motion. Each gyre spins slowly over thousands of miles. In the North Pacific, the gyre turns clockwise, pulling warm water up the Asian coast and cool water down the American side. In the South Pacific, it spins the opposite direction. The Indian, Atlantic, and Southern Oceans all have their own massive spiraling circulations, but the centers of these gyres are still, quiet, and increasingly filled with something unexpected: plastic. The Great Pacific Garbage Patch, located in the heart of the North Pacific Gyre, is not an island of trash, but a slow-moving soup. Millions of tiny plastic fragments, suspended in the water column, drawn inward by the spiraling current. The same gyres that once defined climate now hold the mark of human impact. But even these polluted spirals still host eddies, still breathe, still spin. Some eddies rise from the seafloor, generated when deep currents hit underwater obstacles, ridges, surmounts, slopes. Others are triggered by surface winds, by shear forces, by instabilities in the main currents, and all of them, big or small, follow the strange logic of fluid dynamics. They seem unpredictable, but they follow rules written in math, not intuition. Equations describe how fluids move, how they curl, how a change in temperature, or a nudge from a passing wind, can birth a spiral that lasts for months. But even those equations can't fully predict eddies, because the ocean is nonlinear. Small inputs can cause large disproportionate effects. This is the essence of chaos theory, where systems are deterministic, but unpredictable. A butterfly flaps its wings in Brazil, an eddy forms off the coast of Japan. Not metaphor, physics. The ocean operates on multiple scales, from millimeter-wide ripples to continent-spanning gyres, all layered, all connected. Eddies interact with each other, they merge, cancel out, collide. Their boundaries trap nutrients, particles, even plankton. These boundaries, called Lagrangian coherent structures, act like invisible walls, shaped by math, drawn by water. Scientists now use drifters, satellites and autonomous gliders to trace these spirals. They follow the eddy's path, from its birth to its decay, from hot to cold, from nutrient poor to nutrient rich, and they're learning that eddies are not exceptions. They are the ocean's normal state. Without them, the ocean would be less mixed, less diverse, less alive. Some eddies are warm core. They trap heat, making them buoyant, rising toward the surface. Others are cold core. They push cold water upward, triggering productivity, drawing life toward the sun. Eddies even affect the deep sea. Beneath their rotating bodies, their influence can extend down thousands of meters, stirring sediments, nudging bottom-dwelling creatures, shifting oxygen levels. They are one of the few ways the surface speaks to the abyss, and yet, they're temporary. No eddy lasts forever. They wobble, they decay, they break apart into smaller vortices, or merge into larger systems, but in their lifetime, they act like living beings, born, maturing, interacting, dissolving. In some regions, like the Southern Ocean, eddies dominate the energy of the sea. Hundreds, thousands of them spin at once, like galaxies in a fluid sky. And it's not just Earth. Jupiter's great red spot is an eddy, a storm, yes, but fundamentally a rotating fluid structure, just like our ocean's spirals, just bigger, just longer lived. The physics is the same. Back on Earth, even marine animals use eddies. Sharks, tuna, sea turtles, all use the spinning loops to travel efficiently. They ride the edges where the speed is highest. They feed at the center, where prey gathers. The ocean is not random. It is complex, structured in ways we're only beginning to map. And at the heart of this structure is motion, not linear, but spiraled. Even heat follows the spiral. Eddies help trap warmth or move it across basins. They affect regional climate. They influence rainfall. They matter, but they're fragile. As the climate warms, eddy behavior changes. Their formation zones shift. Their energy intensifies. Their lifespan varies. More heat means more instability, more eddies, more unpredictability, and yet, also more potential. Eddies stir the sea. Without them, the ocean would go still, stratified, layered, unmixed. With them, it stays alive, from the sunlit surface to the midnight bottom. As we drift through one now, the water around us spirals gently, not violent, not loud, just a slow dance of layers. Above, the temperature shifts slightly, below nutrients rise. Even here in the stillness of narration, the ocean moves, not forward, not backward, but around, and just beyond this spiral, a quiet ridge, with a line of chimneys rising, steam rising from stone, a forest of heat and metal. Let's go there. We follow the current downward, spiraling past layers of drifting particles, past suspended plankton, glimmering gelatinous forms, past creatures without names. And then, the water begins to shimmer, not from sunlight, but from heat. A ridge rises before us, jagged, broken, bleeding warmth. Columns of stone stretch upward, like chimneys, venting something dark, inky clouds, gushing into the cold sea. This is not smoke, it is superheated water, bursting from cracks in the Earth's crust, loaded with dissolved metals, minerals, and ancient energy. These are hydrothermal vents, and the blackest, hottest, most mysterious of them all are called black smokers. They are the breath of the seafloor. Here, miles beneath the surface, the Earth's crust splits apart at mid-ocean ridges, like the seams of a planetary scar. Cold seawater seeps down into those cracks, traveling deeper into the crust, where it meets magma-heated rock. The water heats. It dissolves minerals from the surrounding rock, iron, copper, zinc, sulfur, and then, under pressure, it surges back upward, not boiling, because pressure keeps it liquid, but superheated, over 350 BPa. When this water re-emerges through the vents, it hits the cold ocean again. Metals precipitate, minerals solidify, and a black cloud erupts, like underwater smoke. Over time, the minerals build. They form chimneys, tubes of metal sulfide, often several meters tall. Each puff from the vent grows the structure higher, and around them, something astonishing. Life, not sparse, not feeble, but dense, alien ecosystems, blooming in the dark. Here, in the absence of sunlight, life doesn't rely on photosynthesis. It feeds instead on chemosynthesis, a process where microbes use the energy in chemicals, like hydrogen sulfide, to build organic matter. These microbes are the foundation, and everything else grows upward from them. Towering tube worms, Riftia pachyptia, can grow 2 meters long. They have no mouth, no stomach. Inside them lives a symbiotic bacteria colony that digests the vent chemicals and feeds the worm. White crabs crawl over hot rock. Blind shrimp cluster near cracks, sensing heat with specialized receptors. Mussels, clams, squat lobsters, all packed into narrow zones, where the chemical soup is just right. Each species has evolved to survive gradients of temperature, toxicity, and acidity that would kill surface life instantly, and yet, here they thrive. They live in a world where water is both poison and sustenance, where the sun is chemical, and the air is heat, where time runs slowly, and change is constant. Vents can erupt without warning, or shut down, and when they do, entire ecosystems vanish, smothered, frozen, or starved. But new vents open nearby, and within months, life finds them. Like nomads of the deep, these organisms drift in larval form, carried by currents, sensing the faint chemical trails of new chimneys, new homes, new heat. How they navigate this black maze is still unknown. Some scientists believe these ecosystems may resemble the earliest life on Earth, not green and sunlit, but sulfur-fed and heat-borne, primitive cells clinging to hot rock, reproducing in the dark, building complexity one reaction at a time. Here, on Earth, life may have begun in places like, not in shallow pools, but deep in the crust, at the place where rock and water meet, and maybe, beyond Earth, life is doing the same, because the conditions at black smokers bear eerie resemblance to what we see on the ocean moons of Jupiter and Saturn, Europa, Enceladus, Titan. Cracks in icy crusts, subsurface oceans, internal heat, and the chemical ingredients of life. If life exists beyond Earth, it may not be basking in alien sunlight, but thriving in alien dark, around vents just like these. That's why NASA studies Earth's smokers, not just for ocean science, but as analogues for astrobiology. If we understand how life survives here without sun, in poison, under pressure, we open our eyes to the possibility that life is not rare, just different. But even here, there is mystery. Some black smokers host bacteria that survive temperatures above 120 degrees, above the boiling point of water at sea level. Some microbes feed on metals, others on methane. Some even use radioactivity as an energy source. They redefine what life means. Their genes are strange, their proteins twisted, their biochemistry unfamiliar. Scientists sequence their genomes and find enzymes that might someday be used in medicine, or industry, or environmental cleanup. These organisms digest sulfur like we digest sugar. They survive in acid like we survive in air. They teach us resilience. Even their structures are weird. Some microbes form biofilms, layered mats of living tissue that trap metal particles. Others build filaments that bridge mineral grains, creating vast microbial networks across the rock. And the chimneys themselves? They pulse, they grow. Some emit white smoke, lighter clouds of barium, calcium and silicon, a different kind of vent, with different ecosystems. Black or white, every vent is a city, populated by species unknown just a decade ago, still full of creatures we haven't named. Even now, every dive finds more: worms that glow, snails with metal armor, fish that hover in thermal gradients. No light, no photosynthesis, no peace. But still, life. Here, Earth's chemistry becomes alien again, and biology becomes a function of geology. The crust feeds the microbes feed the ecosystem, and everything returns to rock. This is not an oasis, it's a world, and yet, it is temporary. Black smokers don't last forever. They clog, They cool, they die, but the ridge keeps spreading. New vents open, new chimneys rise, new life begins. In some places the fossil remains of old vents called sulfide deposits can be miles wide, testament to life that bloomed and burned out long before humans walked the earth. And some of these deposits we now mine. There is metal here, copper, zinc, rare earth, and some companies want to harvest it. But what life will we lose? What chemistry will we erase before we even understand it? There is a cost to touching the deep. We do not yet know what lives in all these vents. We do not know how fragile their balance is. We do not know what they still have to teach us. But we know this: wherever heat and water meet rock, life finds a way. It builds, it adapts, it invents, not because it wants to, but because it can. As we drift away from the vent field, the smoke thins, the heat fades, but the memory lingers. Something alien was here, and maybe it still is. Up ahead, the ridge narrows again. Beyond it, a whale song echoes faintly through the water, a sound not of rock or metal, but of memory. Let's follow the voice. In the deep sea, there is no light, no color, no shadow, no form, but there is something else. Sound. Where the eye fails, the ear awakens, and in this darkness giants speak. They do not shout, they sing. A single note, stretched over seconds, a rising pitch, undulating through miles of cold black water, an echo from one leviathan to another. This is not noise, it is language, it is memory, it is whale song, and it begins with pressure. In the ocean, sound travels differently than in air. It moves faster, 4 times faster. It bends, refracts, curves through layers of temperature and salinity, and it carries. A low-frequency call from a blue whale can be heard thousands of kilometers away, not just in the next bay, but across basin. There is a special zone in the ocean, a depth band where sound becomes trapped, bouncing between layers with minimal loss. It's called the SOFAR channel, sound fixing and ranging. In this natural duct, low-frequency sounds can circle the globe. Some scientists believe whale calls ride this highway. A whale in the South Atlantic might be heard by another in the Indian Ocean, across half the world. To live in the deep is to listen, and no one listens like a whale. They are built for sound. Their skulls are shaped to channel it, their ears adapted to isolate it. Some species hear in octaves below human hearing. Others pulse out ultrasonic clicks with pinpoint accuracy. They do not just use sound to communicate, they use it to see. This is echolocation, an internal sonar. Click, pause, return. A toothed whale, like a sperm whale or a dolphin, emits a rapid series of clicks. The sound hits an object. It bounces back. The time delay, the strength, the pitch shift, all paint a picture. A whale can see a squid in pitch black, track a school of fish, map the contours of a canyon wall. This is how they hunt, how they navigate, how they survive. Baleen whales like humpbacks and blues do not echolocate, they sing. Their songs are long, structured, repetitive, sometimes lasting over 30 minutes, performed over and over for hours. Each population has its own dialect. Each year the song evolves. New phrases are added, old ones forgotten. It is not instinct, it is culture. When a new song emerges in one part of the Pacific, within a few seasons, whales thousands of miles away begin to copy it, as if a tune had gone viral across the ocean. Why they sing is still debated. Some say it's for mating, a long-distance serenade. Others believe it's for orientation, group bonding, or even emotional expression. But whatever the purpose, one thing is clear: whales listen to each other. They share acoustic space, and in that space, they pass information across distances, across generations. A baby humpback learns its mother's voice, a soft whine, a low moan. It follows that voice through the migration, from cold feeding grounds to warm birthing lagoons. Calves imprint on these sounds, a sonic fingerprint. It guides them even when the mother is gone. Sperm whales use clicks, rapid, powerful bursts of sound, not just for hunting, but for conversation. They form groups, social units, And within those units, coders, short patterns of clicks, like Morse code. Each unit has its own coders, each coder, a symbol of identity. They pass them down like surnames. This is culture, not just biology, not just instinct, but learned behavior, shared, refined, remembered. Whales carry maps in their memories, routes passed from mother to calf, migratory paths, stretching thousands of kilometers. They return to the same breeding grounds, the same feeding areas, following not roads but songs. Sound also tells them about the world. A distant underwater quake, the rumble of a landslide, the distant whine of a ship. Whales live in a soundscape, and lately, that soundscape is changing. The ocean is growing noisy. Cargo ships rumble across the sea, sonar pulses from submarines, oil exploration detonates blasts of compressed air, and this noise, mostly low frequency, overlaps with whale communication. It masks their voices, interrupts their song, forces them to shout louder. Sometimes, it drives them away. In some places, whales have changed the pitch of their calls, adapting to avoid interference. In others, they've gone silent. Some strandings have been linked to sudden acoustic trauma, sonar bursts causing whales to surface too quickly, leading to embolisms. We are altering a world we barely understand, but we are also learning. In recent years, ocean scientists have begun deploying hydrophones, underwater microphones, across the seas. These instruments reveal a planet, humming with life. Whale song, fish choruses, crustaceans clicking in unison. The ocean is not silent, it is a symphony, and whales are its most powerful musicians. We've used these sounds to track migration, to identify individuals, to estimate populations, to detect stress, fear, curiosity, joy. Some researchers have even used AI to decode whale coders, uncovering structure, repetition, possibly even grammar. We are on the verge of understanding whale language, not just in fragments, but as a whole. The idea that one day we might converse with a whale, not just mimic, but truly understand, is no longer science fiction. And if we listen closely, we might already be halfway there, because the ocean speaks, not in words, but in waves, low rumbles, long calls, spiraling clicks in the dark. These are the thoughts of giants. Some live over a century, some dive deeper than submarines, some remember paths from an Earth that was cooler, quieter, wilder. They carry stories in their bodies, in their scars, in their songs, and when we listen, truly listen, we hear a world still singing. Ahead, the water stills, the pitch changes, a whale's final note fades into silence, but beneath us, something rises, not a creature, a mountain, volcanic, alive, and glowing. Let's descend again into the fire. Not all mountains reach the sky. Some rise toward the surface, and never break through. They sleep beneath the waves, silent and unseen, yet they shape the oceans more than most peaks ever shape the land. They are called seamounts, underwater mountains, formed by volcanic fire, lifted from the planet's crust, and then drowned by time. Some are extinct volcanoes, others still burn quietly within, but all of them stand in darkness, rising thousands of meters from the ocean floor. There are more than 100,000 seamounts across the globe. Only a fraction have names. Fewer still have been studied. They are the hidden highlands of the deep, isolated, towering, alive. When you approach a seamount from the abyssal plain, the world begins to shift. The sediment thins, the water stirs. A current touches your shoulder, where before there was stillness. Because seamounts interrupt the flow, they create turbulence, redirecting currents, stirring nutrients, mixing oxygen. They bend the ocean around like a boulder in a stream. They shape everything downstream. Water rushes up their slopes. This is upwelling, when deep, nutrient-rich water is lifted toward the light. And where there are nutrients, there is life. Tiny plankton bloom in the water above. Zooplankton follow. Small fish gather. Larger predators soon arrive. Seamounts become oases, feeding grounds for tuna, sharks, whales, squid. Even migratory birds, far from land, are drawn to the richness above these submerged peaks. Corals grow on their flanks, not the sunlit, shallow kind, but cold water corals, white, skeletal, ghost-like. They anchor to rock. They grow in slow, spiraling fans. Some live for hundreds of years, some for thousands. They form reefs, hundreds of meters tall, cathedrals of calcium, built in silence. Sponges bloom beside them, filtering water, creating homes. Together, they build vertical cities in the dark, and where structure exists, life comes. Fish weave through the coral tower. Octopuses curl inside sponge hollows. Crabs, starfish, eels, all make their homes on the hard slopes, because the deep sea, mostly flat and soft, rarely offers anchor, but seamounts offer foundation. They also offer refuge. For some species, seamounts are the last strongholds, isolated habitats, untouched by trawlers or mining. Others use them as stepping stones, hopping from one mount to the next, across vast distances. Genetic studies show that many seamount populations are distinct, separated by depth, by current, by silence. Evolution happens in isolation. New species emerge, old ones persist, unchanged. But seamounts are not just biological, they are geological monuments. Some rise over 4,000 meters from the seafloor, as tall as the Rockies, yet completely submerged. Many are guyots, flattened by erosion when they once stood above the waves, then slowly sank, as the crust cooled. They are fossil islands, memories of another Earth. Others are newly formed, volcanic cones, still warm, still trembling. Seamounts cluster along mid-ocean ridges, along hotspots along subduction zones, places where the planet reshapes itself. In the Pacific, the Emperor Seamount chain stretches like a backbone across the basin, a trail left by the Pacific Plate, drifting over a mantle plume for millions of years. Each mount marks time, each one a volcanic calendar. Some grow fast, others slowly collapse. Landslides scar their flanks, sometimes causing tsunamis above, and beneath their peaks, hydrothermal vents may lie, chimneys of heat and metal feeding microbial life. Seamounts are crossroads, between geology and biology, between motion and stillness. They alter the very shape of the sea. Oceanographers now use sonar, satellites, and autonomous submersibles to map these peaks. Most were unknown until the last few decades. In fact, many large seamounts remain undiscovered, hiding beneath shipping lanes, beneath migratory routes, beneath regions we assumed were empty. Some were only found when a ship's echo sounder suddenly pinged too shallow, a mountain rising from nowhere. But now we know, the deep is not flat, it is folded, it is rising, it is filled with hidden giants. And with that knowledge comes responsibility, because seamounts attract fish, especially long-lived, slow-growing species like orange ruffy and alphonse. Some of these fish live over 100 years. They gather in dense aggregations, making them easy targets for deep-sea trawling. In just one season, an ancient seamount ecosystem can be destroyed, corals crushed, sponges shredded, life erased faster than it formed, and mining looms ahead. Seamounts often contain cobalt-rich crusts, formed over millions of years as metals slowly deposit onto rock. Companies now eye them for extraction. But what do we lose when we strip the seamount? Not just habitat, not just species, but history. Some seamounts may hold clues to Earth's mantle chemistry. Others may harbor undiscovered microbes, cures, enzymes, insights, and once gone, they don't return. There is no replanting a 2,000-year-old coral, no rebuilding a reef that grew an inch every century. That is the paradox of seamounts. They rise boldly, but they are fragile, strong enough to shape currents, delicate enough to collapse under steel. But we can choose different. Some nations have begun to protect them, establishing marine sanctuaries, no trawl zones, and scientific preserves. Because even in silence, seamounts speak. They tell us how life adapts, how Earth evolves, how depth conceals not absence, but abundance. As we circle the summit now, the current quickens. A school of fish wheels above us, In the distance, a shark patrols the edge, and beneath our feet, solid rock, where once there was molten fire. We descend again, off the slope, into the blue void. Ahead, the water pulses differently. There is no land, no mountain, but something moves. A bloom, a drifting cloud, alive and vast. Let's follow it. It begins with a single flake, not of ice, not of ash, but of life. A sliver of something once living, a broken cell, a piece of shell, a filament of mucus. One becomes two, two becomes a cloud, the cloud becomes a drift, and the drift begins to fall. This is not weather, it is marine snow, the slow descent of organic matter from the surface world to the depth. It is the ocean's silent offering, the memory of light, falling into darkness. Every second, the surface layers of the ocean bloom with life. Phytoplankton, zooplankton, tiny algae, microscopic animals. They feed, they grow, they die, and as they do, fragments break off. Dead cells, fecal pellets, bits of mucus spun into webs called marine gels. Together, these fragments clump. They bind around dust, sand, even microplastics. And they sink. Not quickly. Some fall just a few meters a day. Others descend like feathered snow, drifting down over weeks. But they fall, always, from sunlit shallows, to twilight dimness, to the deep abyss. By the time they reach the deep sea floor, less than 1% of the original biomass remains. But that 1% feeds an entire kingdom. Down here in the darkness, nothing is wasted. What the surface discards, the deep reclaims. Worms uncoil from burrows to catch a single flake. Sea cucumbers spread feathery arms. Crabs climb slowly across sediment, harvesting what's fallen. Even the bacteria wait, breaking down the softest pieces, releasing nutrients into the sediment. This snow never stops. It feeds the world's largest habitat, the benthos, a plain so vast, it stretches across 60% of Earth's surface. And yet it depends on the fall of a few particles. There is no sunlight here, no photosynthesis, only imported energy, a slow rain of the sun's memory. But marine snow is more than food. It's architecture. As particles clump, they form webs, threads that twist and expand, sometimes centimeters wide. These are called marine aggregates. To a passing copepod, it's a floating buffet. To a larval fish, a temporary home. To bacteria, a superhighway of nutrients. Even jellyfish and comb jellies drift among them, pulsing slowly, feeding on what clings. It is a drifting, dissolving reef, made not of coral, but of everything coral leaves behind. And sometimes snow becomes storm. When a massive algal bloom at the surface collapses, millions of cells die in days. The sea turns green, then brown, then cloudy, and then the rain begins. Flake after flake, pellet after pellet, faster, heavier, more acidic. Whole layers of the ocean blanketed in organic fallout. In these moments the deep eats well, but it also suffers. The decay consumes oxygen. Bacteria bloom in excess, and in some places these blooms trigger hypoxia, low oxygen zones that smother bottom life. Even the feast has consequences. But marine snow is not just about death. It is also about transport. A diatom dies at the surface. It sinks. Its shell, made of silica, travels for weeks. When it finally lands, it becomes part of the sediment, building layer upon layer of fossil memory. Over millions of years, these layers become stone. The white cliffs of Dover, fossilized plankton. The deep ocean's history is written in snow, but not all snow is natural. In recent decades, plastic particles have joined the drift. Microbeads, fibers, fragments. They are sticky. They attract bacteria. They bind to organic matter. And they fall, which means that now, even the deep sea, once isolated, pure, untouched, is coated in synthetic snow. Some creatures ingest it, mistaking it for food. Others incorporate it into their burrows. It is a quiet, slow pollution, not spilled, but drifted. And yet, life continues. Because marine snow is resilient, a system built on decay, yet endlessly renewing. Each spring, new blooms rise in the sunlit surface, phytoplankton bloom. As light returns, zooplankton chase them, fish spawn, jellyfish pulse upward, and as the season ends, the fall begins again. It is the ocean's breath. Inhale in bloom, exhale in snow. This process connects surface to deep, pole to equator, death to life. It is part of the biological pump, one of Earth's greatest climate regulators. As plankton grow, they absorb carbon dioxide. When they die and sink, some of that carbon is sequestered, locked away for centuries in the deep sea. Marine snow helps slow the planet's warming. It is not flashy, it is not loud, but it is powerful. Each flake a message. This life matters, this death nourishes, this moment continues. And drifting among it all, are the drifters, plankton, from the Greek planktos, wanderer, tiny translucent creatures that float wherever the current takes them. Some are animals, some are plants, some defy both labels. There are salps, gelatinous tubes that pump water through their bodies, glowing with inner light. There are pteropods, sea butterflies with delicate wings of calcium. There are larvae of things yet to grow, fish, crustaceans, jelly, and among them, the oldest forms of life on Earth, bacteria, archaea, drifting through time. They do not seek, they do not steer, they simply move and feed, and fall. Some will become part of the snow, some will become predators, some will find a home, on a falling flake, a miniature world, and a few will drift all the way to the bottom, and bloom again, because even in the deep, even in the stillness, there are bursts of color, of growth, of light. Deep sea blooms are rare, but they do happen, triggered by sudden nutrient pulses, from a fallen whale, from an underwater landslide, from a bloom collapse above. Then, in a place where nothing grows fast, life erupts, tube worms sprout, anemones sway, sponges unfurl, and all around, the snow keeps falling. As we hover in this drifting storm, the light around us dims even further. There's a pressure behind us, gentle, rhythmic, not a mountain, not a current, but a pulse, a throb, a rhythm. Let's move toward it. Pressure. It is the silent pulse of the deep, invisible, constant, unyielding. For every 10 meters you descend beneath the waves, pressure increases by 1 atmosphere, the weight of the air pressing down on you at sea level. At the surface, pressure is light, breathable, easy, but descend to the abyss, 4,000, 6,000, even 10,000 meters, and the pressure becomes crushing, thousands of times greater than what we experience on land. It is a force, unlike any other, a weight pressing on every cell, every molecule, every breath. Yet life persists, and more than that, it thrives. How? To answer that, we must first understand what pressure does. Pressure compresses. It forces molecules closer together. It changes the shape of proteins, the building blocks of life. It alters chemical reactions. Under pressure, gases dissolve more readily in liquids. Water behaves differently. Membranes become rigid. Enzymes slow or fail. It is a world transformed, but creatures of the abyss have evolved remarkable adaptations. Their proteins are structurally different, designed to resist unfolding under pressure. Their membranes contain special lipids that maintain fluidity despite compression. Some produce molecules called piezolites, natural pressure protectants that stabilize cells and enzymes. Many deep-sea fish lack swim bladders, gas-filled organs used for buoyancy, because gas compresses under pressure. Instead, they have oily livers and flexible bodies that help them float. Others produce antifreeze proteins to survive near freezing temperatures. Pressure also shapes behavior. Many abyssal creatures are slow-moving. Their metabolisms adapted to conserve energy. They wait, they watch, they take what they can. Life is a slow dance. Yet, the deep sea is not uniform. Pressure increases with depth, yes, but local conditions, such as cold seeps, hydrothermal vents, and oxygen minimum zones. Add complexity. Organisms must navigate a shifting landscape of extremes. Some live at the edge of survivability, where pressure nearly overwhelms them. Others find refuge in niches where pressure fluctuates, and this pressure affects more than biology. It influences geology. It controls the chemistry of sediments. It regulates the formation of minerals. Under immense pressure, certain chemical reactions become possible, reactions that would never occur at the surface. This is why deep-sea methane hydrates exist, ice-like crystals trapping methane gas under high pressure and low temperature. They store vast amounts of carbon, and their stability depends entirely on pressure and temperature. If disturbed, these hydrates can release methane, a potent greenhouse gas, into the atmosphere. Pressure holds the deep sea's secrets tightly. It also shapes sound. As we heard in earlier chapters, sound travels faster and farther in the deep ocean, guided by pressure and temperature gradients. Pressure bends sound waves, trapping them in channels. It muffles noises. It enhances others. For whales, pressure defines their acoustic world. For microbes, it defines their chemical one. For all life, it defines their existence. We humans are fragile in this world. Our bodies are not built for it. Without special vessels, we would be crushed in an instant. But the deep-sea explorers, from the early bathyscaphe Trieste to modern submersibles, brave this pressure. They descend into an alien realm, where time slows, and the rules change. And they bring back glimpses of life shaped by the heartbeat of pressure. As we drift in this realm, we feel it too. A rhythm, a pulse, a silent reminder of the power pressing around us. The ocean is alive, not just with life, but with force. Pressure is its heartbeat, and it shapes every moment. Ahead, something shifts, a faint glow, a flicker in the darkness, a living pulse. Let's move closer. In the deep ocean, darkness reigns supreme. No sunbeam pierces the abyss. No colors shimmer beneath the waves. Yet the ocean is alive with light, ethereal, fleeting, alive. This light is not borrowed from the sun. It is born within, a glowing, breathing fire in the cold deep. This is bioluminescence, the creation and emission of light by living organisms. Imagine a world where light is rare and precious, where survival depends not on sight, but on the flicker of a glow. Here, over 80% of deep-sea creatures possess the power to shine, from microscopic bacteria, tiny plankton, to giant squid and mysterious fish. Life illuminates the darkness in dazzling variety. The chemistry behind bioluminescence is a marvel of evolution. Within cells lie special molecules called luciferins, chemical keys that, when combined with oxygen in the presence of enzymes called luciferases, ignite in a flash of photons. This reaction requires energy, ATP molecules fueling the glow, but the payoff is vital. The emitted light spans a palette of colors, mostly blues and greens, because these hues travel the furthest through water, penetrating the darkness with ethereal grace. Occasionally, red or yellow light appears, a secret code for those few that can see it, a hidden language beneath the waves. Bioluminescence is nature's flashlight, lantern, warning sign and seduction, all at once. Consider the delicate art of camouflage. Above, where faint light filters down from the surface, predators look upward for silhouettes, shadows against the light. Many deep-sea creatures evade this fate through counter-illumination. They produce light on their bellies that matches the faint glow above, erasing their shadow and becoming nearly invisible. It is a trick of light and shadow, an ancient dance of survival. But light is also a lure. The infamous anglerfish dangles a glowing appendage, a bioluminescent lure before its enormous jaws, enticing curious prey into the fatal embrace. Squid emit rhythmic flashes that can hypnotize or confuse. Jellyfish pulse waves of light to communicate or detect. Some animals deploy brilliant bioluminescent clouds, like ink, to obscure themselves from predators. Others use light as a territorial signal, or mating call, flashing complex patterns that hint at social interaction beneath the waves. These displays are not random, they follow intricate patterns. Some species synchronize their flashes in vast underwater ballets, thousands of creatures blinking in unison, creating a symphony of light that can last for hours. This bioluminescent chorus is one of nature's most haunting spectacles, a silent symphony in the abyss. Bioluminescence also reveals ecological truths. In this light, creatures communicate across the inky blackness. They navigate complex food webs. They find mates. They warn rivals. Some use red bioluminescence to hunt covertly. Their prey can't see red, so the predator shines a secret flashlight. Others use blue-green light to dazzle or distract. The shapes of light vary too. Some produce steady glows. Others flicker rapidly. Some flash. Some glow softly like embers. Others pulse rhythmically like beating hearts. Each pattern carries meaning, and bioluminescence is ancient. Fossil records and molecular clocks suggest that this glowing ability evolved over 500 million years ago, one of the earliest adaptations to life in dark water. It's a trait passed through countless lineages, convergent evolution, showing how vital light is in the depth. Even some microbes glow. Bioluminescent bacteria live in symbiosis with larger animals, firing light for their hosts. In exchange for shelter and nutrients, they colonize the light organs of fish, squid, and crustaceans, turning their bodies into living lanterns. This glowing partnership is essential. Without their bacterial partners, many deep-sea animals would lose their light and the survival advantages it brings. Bioluminescence also plays a role in predator-prey dynamics. Predators use it to locate prey. Prey use it to escape. When attacked, some fish release luminous mucus, a glowing smoke screen. Others flash blinding bursts to confuse. The light may even act as a last warning, a signal to larger predators that the prey is toxic or unpalatable. The ocean itself is punctuated by bioluminescent light. Waves glitter at night as dinoflagellates glow when disturbed. Sea jellies and siphonophores flash and flicker, drifting like stars in a dark sky. This light is not constant. It varies by season, by location, by moon phase, and it depends on life cycle. In some places, bioluminescent blooms rise, massive congregations of tiny glowing organisms, turning water into liquid stars. Scientists study these light shows not just for beauty, but for clues about ecosystem health and change. Bioluminescence is also inspiring human innovation. Its chemistry informs medical imaging, where glowing markers trace cancer cells. It inspires new materials that light without electricity. It guides the search for life on other worlds, because light may be the first sign of life in alien ocean. Despite decades of research, bioluminescence holds mysteries. How do animals control the color, intensity, and pattern? How do they coordinate mass displays? How does light influence deep-sea behavior? New technologies, sensitive cameras, submersibles with low-light sensors, genetic sequencing, are revealing secrets. Yet much remains hidden, because the deep sea resists easy observation. Every glow is a whisper, every flash, a secret. And for all its darkness, the ocean is alive with light. As we float here, surrounded by a shifting mosaic of glows, pulses and sparks, we sense something profound. Life in darkness is not silent, it is not empty. It sings in photo, and the language it speaks, glowing, flickering, swirling, connects the past and future, predator and prey, light and life. Ahead, the glow fades slightly, a shadow moves, not light, a shape, something living. Let's follow it. In the eternal darkness of the deep ocean, silence is power. Movement must be stealthy, senses must be sharp, energy must be precious. Here the hunters are silent. They move through black water with ghostly grace, their bodies sculpted by pressure, hunger, and time. The deep sea is not a place of abundance. It is a realm of scarcity. Food falls slowly from above. Prey is rare. Predators must be efficient, and so life evolves. To hunt in the deep is to master patience, precision, and surprise. Many deep-sea predators have evolved elongated, streamlined bodies, perfect for sudden bursts of speed. Some have hinged jaws, capable of unhinging to swallow prey larger than themselves. Teeth are sharp, needle-like, designed to grip slippery, elusive targets. Take the viperfish. Its jaw juts forward like a trap, lined with translucent fang-like teeth so long they curve past its eyes. It waits in the dark, motionless, then strikes with lightning speed. Or the gulper eel, with a mouth so large it can engulf prey as big as itself. Its stomach can expand to accommodate unexpected meals. Others use light to hunt. The anglerfish's glowing lure is not just a beacon, it is a tool of deception. Wriggling like a worm, it tempts curious fish close enough to be snapped up. Some species produce their own light, glowing patches to illuminate prey, or to communicate with potential mates. In a world without sight, sound and vibration also matter. Many deep hunters have lateral lines, sensitive canals running along their bodies detecting movement, pressure waves, and vibrations in the water. Some produce low-frequency sounds to stun or confuse prey. Others sense electrical fields generated by muscle contractions. Because in darkness, every sense must be heightened. Adaptations go beyond hunting. Some predators are sit-and-wait specialists. They conserve energy by remaining still for hours. Others are active hunters, patrolling wide territories. Because food is scarce, metabolism is often slow. Deep-sea sharks, for example, have low metabolic rates, swimming slowly, feeding opportunistically. Many deep predators are small, but some grow surprisingly large. The giant squid, rarely seen, can reach lengths of 13 meters or more. Its massive eyes, the largest in the animal kingdom, are tuned to capture the faintest light. They hunt in pitch blackness using sharp hooks and powerful tentacles. Sperm whales in turn dive thousands of meters to hunt these elusive giants. Some fish exhibit transparency or extreme camouflage. Glass squids, with translucent bodies, become nearly invisible in the water. Others display counter-illumination, blending with faint surface light. The black dragonfish sports photophores, light-producing organs on its chin and fin. These serve as bait and communication. The gulper eel has bioluminescent organs along its body, creating a surreal glow in the dark. Adaptations also reflect the need to find mates in a vast, dark world. Many deep-sea fish are sexually dimorphic. Males are tiny and attach permanently to larger females, becoming living parasites to ensure reproduction. Some species produce pheromones or flashes to signal readiness. Others have evolved enormous eyes or sensitive organs to detect the faintest hint of a mate. Survival in the deep is a balance between energy conservation and opportunistic feeding. Predators take advantage of every opportunity. Some species scavenge, feeding on the remains of whales, fish, or other animals. The whale fall ecosystem, when a whale dies and sinks, becomes a banquet lasting years, supporting a succession of scavengers and predators. These falls are rare but vital, temporary oases of abundance in the deep. Predators also navigate complex terrain. Ridges, surmounts, trenches, all shape movement and hunting grounds. Many predators patrol the edges of currents where prey concentrate. Others hunt near hydrothermal vents, where unique ecosystems thrive. Despite harsh conditions, predators here show extraordinary diversity, from dragonfish to cookie-cutter sharks, from giant squids to fangtooths. The abyss holds creatures both terrifying and fascinating. Their adaptations challenge our ideas of life, showing resilience, innovation, and the will to survive. As we drift through this silent realm, we glimpse the balance of the deep, predator and prey, light and dark, stillness and motion. Ahead, the water shifts, a glow fades, and a shadow passes. Let's follow it. The deep ocean is a world ruled by darkness and pressure, a realm where light never penetrates, and where silence is both a necessity and a weapon. Here, survival demands remarkable adaptations, and life exists on a razor's edge, balanced between scarcity and opportunity, between invisibility and sudden violence. The hunters of the deep sea are masters of stealth, evolving bodies and behaviors fine-tuned to this harsh environment. They move with ghostly grace, their forms sculpted by the unrelenting forces of crushing pressure, freezing cold, and eternal night. Food is rare, The deep ocean is not a place of abundance, but of patient waiting. The hunters here rely on ambush, surprise, and ingenious strategies. Their prey is often scarce and elusive, forcing predators to be efficient with every movement, every calorie consumed. Consider the extraordinary diversity of their forms. Many deep-sea predators possess elongated, streamlined bodies, perfectly adapted for rapid bursts of speed that capture the unexpected. Their jaws are often hinged and flexible, capable of unhinging to swallow prey larger than themselves, a crucial advantage in an environment where meals are few and far between. The viperfish is one such hunter. Its jaw juts forward like a predatory trap, lined with fang-like teeth so long they curve backward past its eyes, preventing any prey from escaping. It waits in the pitch-black darkness motionless, until a target approaches, then strikes with lightning speed, a brief flare of activity in an otherwise slow world. Then there is the gulper eel, with a mouth so immense it can engulf prey its own size. Its stomach can expand dramatically, allowing it to feast on whatever it finds. The gulper eel drifts quietly through the abyss, ready to seize any opportunity, a living testament to opportunism in a landscape of scarcity. Some deep-sea predators wield light as a weapon or tool. The anglerfish famously dangles a glowing lure, a bioluminescent appendage, before its massive jaws enticing curious prey close enough to be devoured. This flickering light is the only sign of life in the surrounding darkness, a beacon that both attracts and deceives. Others generate their own light, producing glowing patches that illuminate prey or communicate with potential mates. In the ocean's eternal night, bioluminescence becomes a language, a signal, and a weapon. Silence is paramount for hunters. Movement creates disturbances in the water, pressure waves, and vibrations that potential prey can detect with acute sensitivity. To counter this, many predators possess lateral lines, sensory canals running along their bodies that detect changes in water pressure and movement. These lateral lines function like an invisible radar, allowing predators to sense prey without relying on sight or sound. In addition to lateral lines, some deep-sea predators possess the ability to detect electrical fields generated by muscle contraction. This electrosensory ability provides an advantage in near-total darkness, enabling predators to locate prey hidden in the sediment or cloaked in shadows. The sensory adaptations extend beyond detection. Many deep-sea fish have enormous, highly sensitive eyes adapted to the faintest glimmers of bioluminescence. The giant squid, for instance, has the largest eyes in the animal kingdom, capable of gathering the scarce photons that reach the abyss, allowing it to hunt efficiently in the dark. Behaviorally, many deep-sea predators adopt strategies to conserve energy. The scarcity of food means that quick bursts of activity must be balanced with long periods of rest. Some species employ a sit-and-wait approach, remaining motionless for hours, conserving precious energy until an unsuspecting meal drifts within reach. Others are active hunters, patrolling wide territories with slow, deliberate movement. Their low metabolic rates reflect this energy economy, and their bodies are often soft and flexible, adapted to withstanding the intense pressure while maximizing efficiency. Reproduction in the deep sea presents another set of challenges. The vastness and darkness make finding mates difficult. As a result, many deep-sea fish exhibit sexual dimorphism. Males are often much smaller, and may attach permanently to the females, becoming parasitic mates that ensure reproduction in a lonely world. Chemical signaling, pheromone release, and bioluminescent flashes also play roles in attracting mates across the abyss. Predators in the deep sea are not just hunters, they are scavengers too. The sinking carcasses of whales, fish, and other animals create whale falls, temporary oases of abundance in the deep. These falls support a succession of scavengers and predators for years, from hagfish to giant amphipods to sleeper sharks. They represent rare but vital moments of plenty in an otherwise austere ecosystem. Terrain shapes hunting strategies. Seamounts, ridges, trenches, and hydrothermal vent fields provide habitats and hunting grounds. Many predators patrol these edges, where currents concentrate prey. Despite the extreme conditions, the diversity of deep-sea predators is astounding. From the cookie-cutter shark, a small but fearsome fish that bites chunks out of larger animals, to the black dragonfish with its glowing chin barbel, from the fangtooth with its oversized teeth, to the elusive giant squid, the abyss is home to a menagerie of evolutionary marvels. These adaptations challenge our understanding of life's limits. They show resilience, creativity, and an indomitable will to survive in a realm most of us will never see. As we drift through this silent world, we witness the delicate balance between predator and prey, light and dark, stillness and motion. Ahead, the water shifts, a glow dims, a shadow passes. We follow. The deep ocean is a realm cloaked in shadow and silence, a vast cathedral of stillness where the usual tools of communication, sight, sound, color, are profoundly altered or absent altogether. Yet, life here is far from mute or isolated. Instead, it speaks in whispers and flickers, in vibrations and chemistry, in movements too subtle for the human eye or ear. The symphony of the deep is a complex, multi-layered language that transcends what we understand as communication. At the surface, where sunlight bathes the sea, life relies heavily on vision and sound. Fish flash colors, dolphins click and whistle, whales sing haunting melodies that travel thousands of miles. But as we descend into the abyss where darkness is absolute and pressure immense, the rules change. In this world, creatures have evolved extraordinary strategies to communicate, sense, and interact, often in ways that seem alien to us. Bioluminescence, the ability to produce and emit light, is perhaps the most visible form of communication in the dark ocean. Over 80% of deep-sea creatures possess this glowing gift, turning the abyss into a dance floor of shimmering patterns and flashes. But bioluminescence is only one part of a far richer language. Here we explore the hidden conversations that happen beyond sound, beyond light, in the deep's eternal silence. One key medium is vibrations, subtle pulses and waves that ripple through water and sediment. Many deep-sea animals possess specialized organs sensitive to mechanical disturbances. These vibrations travel faster than sound in some contexts, and can be detected even when sound is muffled by the thick, cold water. For instance, certain species of deep-sea worms tap rhythmically on their tubes, creating mechanical signals that neighboring individuals can perceive, allowing them to coordinate behaviors or signal presence without making noise. In addition to vibrations through water, some communication happens through substrate-borne waves, vibrations transmitted through the ocean floor's sediment. These signals can be crucial for animals living in or on the seabed, such as crustaceans and polychaetes, helping them detect approaching predators or mates through the gentle tremors that precede movement. Chemical communication forms another vital channel. In the cold, dark ocean, scent carries far and wide. Many organisms release pheromones or other chemical messengers into the water, broadcasting messages of danger, mating readiness, or territorial claim. These chemical signals drift slowly with currents, reaching receptive receptors on other creatures who decode the message. The complexity of chemical signaling in the deep remains a frontier of marine biology, but it is clear that this invisible language plays a crucial role in the survival and reproduction of abyssal life. Beyond chemistry and vibration, movement itself becomes communication. Subtle gestures, postures, or changes in swimming patterns convey information. The gentle swaying of corals, the flick of a fin, or the curling of an appendage can warn, attract, or deter. In a world where sight is limited to bioluminescent flickers, these movements are a silent ballet, a dance of signals woven through the dark. Another fascinating form of communication in the deep ocean is electroreception, the ability to detect electrical fields generated by muscle contractions and nerve impulses. Some deep-sea fish and sharks possess specialized organs that pick up these weak electric signals, allowing them to locate prey or navigate in total darkness. This sensory capability provides a private conversation channel, inaudible and invisible to most other creatures. Even the electromagnetic environment itself fluctuates subtly, influenced by geological and biological processes. Researchers have begun to explore how deep-sea life might exploit or respond to these electromagnetic cues, revealing yet another layer of the ocean's secret symphony. Studying these hidden languages is challenging. The extreme conditions of the deep sea, crushing pressure, near freezing temperatures, utter darkness, make direct observation difficult. Advances in technology, however, are opening new windows into these secret worlds. Sensitive hydrophones capture sounds both audible and ultrasonic. Accelerometers and vibration sensors detect the faintest pulses in water and sediment. Chemical sensors identify trace pheromones and organic compounds. Low-light cameras record bioluminescent displays in unprecedented detail. By deploying networks of these instruments, scientists have begun to map the intricate communication web of the deep ocean, a social network composed not of voices or faces, but of light flashes, vibrational pulses, chemical gradients and electric fields. This web connects predator and prey, mates and rivals, solitary hunters and communal dwellers in a complex dance of survival. Yet much of this symphony remains unexplored. The deep ocean, covering over 70% of Earth's surface, is still one of the least understood environments on the planet. Many species remain unknown, and their behaviors and interactions are mysteries. The silent languages they speak are only beginning to be heard. Understanding these communication channels is not just a matter of curiosity, it is essential for conservation. As human activity, shipping, resource extraction, noise pollution, increasingly intrudes upon the deep sea, we risk disrupting these delicate conversations. The loss of communication can have cascading effects, impacting reproduction, hunting, and ecosystem balance. For now, as we float in the dark, surrounded by the quiet symphony of the abyss, we glimpse the profound complexity of life, adapted to silence and shadow. It is a world where every flicker, every pulse, every movement carries meaning. A world where connection transcends the senses we know. Ahead, a faint bioluminescent glow pulses steadily. A subtle vibration hums beneath the water. The chemical scent of life lingers on the currents. Let us follow these signals, these whispers of the deep, onward into the next chapter of our journey. The ocean depths may seem a barren wasteland to the untrained eye, an endless void of darkness and crushing pressure. But beneath that seemingly empty expanse lies a sprawling metropolis, a city forged by life itself. Here creatures of unimaginable variety build, craft, and engineer homes and habitats, adapted to the alien conditions of the abyss. In this chapter, we journey into the realm of the deep sea. Architects, the builders who defy the odds to create shelter, security and community far from the sunlit surface. Most of us associate coral with tropical reefs, vibrant, colorful ecosystems alive with sunlight and diversity. But far below the sun's reach, cold water corals create their own majestic structures. Unlike their shallow cousins, these corals grow slowly, layer by painstaking layer, crafting intricate skeletons of calcium carbonate that tower silently in the darkness. These cold corals form underwater forests and thickets on rocky seamounts, continental slopes, and deep fjords. Some species grow as bushy branching formations, while others spread as massive mounds or pinnacles, rising hundreds of meters above the seabed. In their stillness, these coral structures become pillars of life, oases amid the abyssal plains where soft sediments dominate. Within the branches of these silent cathedrals, countless fish find shelter. Crustaceans weave their way through coral branches. Sponges cling to every available surface. Even delicate brittle stars grasp onto the coral's hard skeleton. These cold coral forests are hotspots of biodiversity, supporting complex food webs and acting as nurseries for many deep-sea species. The growth rates of these cold water corals are slow, often measured in millimeters per year, but their resilience is profound. Some colonies are thousands of years old, standing as living monuments to endurance in one of Earth's harshest environments. Sponges are among the oldest multicellular organisms on Earth, and in the deep sea, they play vital roles as ecosystem engineers. Their porous bodies are marvels of biological architecture. Filtering vast volumes of seawater daily, deep-sea sponges cleanse the water of particles, bacteria, and detritus. Their skeletons are formed from siliceous or calcareous spacules, tiny mineral rods and needles, arranged in intricate framework. These skeletons create mazes, tunnels and chambers, which become homes for a host of tiny creatures, amphipods, polychaete worms, small crustaceans, and juvenile fish find refuge within the sponge's labyrinthine body. Some sponge species form dense grounds or fields, sprawling expanses carpeting seamounts and continental slopes. These grounds alter the local environment, influencing water flow, sediment deposition, and nutrient cycling. In effect, sponges shape their own neighborhoods, enhancing biodiversity and ecosystem resilience. Sponges grow slowly, and their fragile skeletons can be easily broken by strong currents or human activity. Their architecture may be delicate, but it is essential. Near hydrothermal vents, deep-sea tube worms create some of the most striking structures of the abyss. These worms build protective chitinous tubes that extend upward from the seafloor, forming dense aggregations sometimes called forests of fire. These tubes serve multiple purposes: shelter from the scorching vent fluids, protection from predators, and support for symbiotic bacteria living inside the worm's body. These bacteria use the chemical energy from vent fluids, rich in hydrogen sulfide, to produce organic matter, feeding their hosts and sustaining the vent community. The tubes themselves become habitats for other species as well. Small crustaceans, mollusks, and even fish shelter among these tubular towers. Over time, these structures can grow meters high, creating vertical habitats that rise above the barren rocky floor. Tube worm aggregations exemplify a complex symbiosis between geology, chemistry, and biology. The worms build homes where few others can survive, transforming inhospitable environments into bustling ecosystems. Not all deep-sea architect build with mineral skeletons or secreted tubes. Many creatures are skilled at repurposing their environment to fashion shelter. Deep-sea octopuses, for example, are known to collect shells, stones, and even man-made debris, glass bottles, cans, and other lost objects, to create dens and protective hideouts. These dens offer vital protection from predators and harsh currents. Some octopuses carry their homes as they move, a mobile fortress against the dangers of the dark. This behavior reflects remarkable intelligence and adaptability, showcasing an active architectural approach rather than passive growth. Crabs and other crustaceans also collect materials, arranging them into protective structures or camouflaging themselves with attached debris and organisms. Some hermit crabs modify their borrowed shells, enhancing protection or adapting to their needs. Some deep-sea worms produce silky threads to weave webs or nets, capturing suspended particles from water currents. These structures, though delicate and ephemeral, are essential feeding platforms and micro-habitat. The drifting nets can be meters long, filtering food in nutrient-poor environments. Mucus secretions also play a role. Some species produce mucus tubes or nets that trap detritus and plankton, allowing them to feed efficiently. These mucus constructions can form complex habitats that persist for months or years. At a microscopic level, bacterial biofilms represent some of the simplest yet vital architects of the abyss. These thin living layers adhere to rocks, sediments, and animal surfaces, trapping nutrients and forming the base of many food webs. Biofilms contribute to mineral precipitation and geochemical cycles, helping to shape the seafloor's physical and chemical landscape. Many deep-sea organisms live by burrowing into soft sediments, crafting complex tunnel networks and chambers. These burrows offer protection from predators, buffer against environmental changes, and serve as nurseries for offspring. The act of burrowing, called bioturbation, dramatically influences sediment structure, oxygen penetration, and nutrient cycling. Burrowers rework the seafloor, mixing organic matter and sediments, fostering microbial life, and creating habitats for other species. Some burrows can extend meters below the surface, with intricate branching and multiple entrances, demonstrating sophisticated engineering skills. Deep-sea creatures employ mineral deposition not only for building homes, but also for creating armor and protection. Many bivalves, gastropods, and crustaceans reinforce their shells with minerals like calcium carbonate or iron sulfides, strengthening defenses against predators and physical stresses. These mineralized structures vary widely, from simple smooth shells to complex ornate spines and ridges, reflecting evolutionary pressures and ecological niches. Some species can even modify mineral composition in response to environmental conditions, showcasing a dynamic relationship between biology and geology. Beyond individual shelters, deep-sea creatures construct communal habitats that sustain entire ecosystems. Sponge grounds and cold coral reefs form dense, living neighborhoods teeming with life. Hydrothermal vent communities cluster around chimneys, where animals modify chemical gradients and water flow, creating microhabitats for symbiotic species. These ecosystem engineers play crucial roles in maintaining biodiversity, enhancing habitat complexity, and fostering resilience. By shaping their environment, these builders enable life to flourish in seemingly inhospitable conditions. Building in the abyss is a slow process. Growth rates are often measured in millimeters or centimeters per year. Corals may take centuries to form extensive reefs. Sponges grow over decades or centuries. Maintaining these structures requires constant adaptation to shifting currents, sediment deposition, and biological interaction. Energy is scarce, and investment in construction must be balanced with survival needs. Despite these challenges, deep-sea architects persist, crafting habitats that endure geological time. The fragile architectures of the deep ocean face growing threats from human activity. Bottom trawling can devastate coral forests and sponge grounds in minutes, destroying habitats formed over centuries. Deep-sea mining targets mineral-rich seamounts and vent fields, risking irreversible damage to unique community. Conservation efforts increasingly recognize the need to protect these living cities. Marine protected areas, no-trawl zones, and international agreements aim to preserve these habitats. Scientific research helps inform management, revealing the ecological and evolutionary significance of deep-sea architects. As we descend into the deep sea's living cities, we see a world of complexity, resilience, and wonder. Far from barren, the abyss is shaped by countless architects, creatures that build homes of stone, silk, mucus, and mineral, that engineer ecosystems and foster life in darkness. These habitats tell stories of survival, adaptation, and interconnection across time and space. The deep sea is not a silent void but a sprawling metropolis, crafted and sustained by life itself. As we float through this realm, the pulse of creation beats steadily beneath the waves. Ahead, the current shifts, carrying nutrients and life. New structures rise from the darkness. Let us follow. The ocean is not still. Though its surface may appear calm, beneath it pulses a relentless rhythm, a hidden heartbeat that never stops. These are the currents of the deep, silent rivers flowing through liquid darkness, shaping the very foundation of life far below the waves. In the absence of sunlight, where the sea becomes a cathedral of cold and pressure, there are no winds to stir the waters, and yet the ocean moves. It breathes, it circulates, and within this movement lies the key to everything that lives in the deep. These currents are not chaotic, they are precise, ancient, and powerful. They whisper across vast distances from one corner of the planet to another, guiding life in all its fragile, remarkable forms. The deep sea is often described as isolated, remote, disconnected from the living surface world, but that is a misunderstanding. The deep is not alone. It is bound to the surface by threads of motion, carried by thermohaline currents, tidal flows, seafloor topography, and planetary forces. Together, these patterns create a vast, interconnected system, one so complex and powerful that it defies simple comprehension. At the heart of this system is something scientists call the global conveyor belt, the thermohaline circulation. Driven by differences in temperature and salinity, this process begins in the polar regions, where cold, salty water becomes dense enough to sink. This sinking water slowly creeps along the seafloor, forming deep currents that circle the globe like an ancient procession. These currents can take centuries to complete a full cycle, but their impact is immediate and profound. They carry oxygen, nutrients, and heat across basins. They bring surface energy down into the dark, feeding entire ecosystems that have never seen the sun. They stir sediments, push life toward ridges and rises, and deliver chemical signals that trigger migration and growth. But these aren't the only forces at work. Tidal currents, generated by the gravitational pull of the moon and sun, echo through the ocean like breath through lungs. In the deep sea, where tides don't manifest as waves or beach movements, they appear as subtle oscillations, slow surges of water that drift back and forth over time. These movements may be small, but their influence is great. They shape the flow of nutrients, transport larvae across canyons, and modulate temperature in ways that affect species over generations. Then there are contour currents, slender, persistent streams of water that hug the contours of the seafloor, tracing the edges of continental slopes and submarine ridges. These currents, often overlooked, are vital sculptors of the deep. They erode sediments, carve channels, and create habitat zones where life clusters in unexpected abundance. Where currents meet topography, where a deep stream strikes a seamount or collides with a trench, something extraordinary happens. The water lifts, it churns, it spirals upward. In this process known as upwelling, nutrients buried in the depths are brought to shallower zones, triggering blooms of plankton that ripple up the food chain. And in reverse, downwelling currents drag surface particles and oxygen downward, ensuring that the deep sea receives not only food but breath, vital oxygen that sustains aerobic life in the abyss. Even on the abyssal plains where the seafloor stretches in still, cold silence, currents do not rest. They drift gently across sediments, sorting particles, carrying marine snow, and whispering life into place. This marine snow, a slow, steady rain of organic debris, is often the only source of nourishment for creatures that dwell in these deep expanses. It is transported by gravity, yes, but also guided by current. Without these invisible rivers, the snow would drift unevenly, lost to chance. With them, it finds its way everywhere. Deep-sea animals have evolved to understand these rhythms. Tube worms, sea cucumbers and brittle stars align themselves with prevailing flows to better catch food. Deep water corals grow in fan-like patterns that maximize current exposure. Sponges open their porous bodies to absorb nutrients carried on passing streams. And filter feeders, those patient dancers of the current, rely entirely on these movements to deliver sustenance to their waiting arms. Currents are also couriers of life. Many deep-sea creatures release their offspring into the water column, tiny larvae meant to drift and disperse. These delicate beginnings are helpless on their own, but the currents carry them to new places, spreading genes, colonizing new habitats, and maintaining population resilience. Without these movements, deep-sea biodiversity would shrink, species would become isolated, the web would fray. But not all currents bring life. Some bring change, others bring danger. In parts of the ocean, particularly between 200 and 1,000 meters in depth, lie what scientists call oxygen minimum zones (OMZ), vast layers where dissolved oxygen is scarce. These zones are shaped in part by currents, which may fail to bring sufficient oxygen to balance what's consumed by bacteria and decaying material. In these stretches, life must adapt or flee. Creatures evolve to survive with little oxygen, altering their metabolisms, gill structures and behaviors to endure what others cannot. Meanwhile, mesoscale eddies spinning, circular currents hundreds of kilometers wide act like slow rotating storms within the ocean. Some bring warmth and nutrients to places that need them, others trap life within them for weeks or months, changing local food webs and altering species interactions. These eddies, though temporary, leave long-lasting marks on deep-sea communities. On a much smaller scale, microcurrents swirl around individual rocks, corals and organisms. These tiny flows influence settlement patterns for larvae, distribute chemical cues, and define microhabitat. Even a small shift in current direction can mean the difference between a successful colony and an empty wasteland. Deep ocean currents are also shaped by geothermal forces. Around hydrothermal vents, superheated water bursts from the seafloor, creating turbulent updrafts that mix with surrounding cold seawater. These plumes rise, cool, and eventually fall, setting up localized convection loops. In these vent fields where chemical energy replaces sunlight as the fuel of life, currents become the carriers of sulfur, methane, and other vital compounds. They determine where chemosynthetic bacteria thrive, which in turn determines where everything else lives, from tube worms to crabs to vent-dwelling fish. Currents also shape the geography of the seafloor. Over millennia, their steady flow sculpts canyons, deposits sediments in layered drifts, and exposes rocky outcrops. These processes create structure, and where there is structure, life can take hold. In these underwater landscapes carved by current, biodiversity flourish. Cold water coral reefs grow in places where currents concentrate nutrients. Sponge grounds form dense mats where water movement ensures constant filtration. Schools of deep-sea fish gather where eddies trap prey. The current does not merely pass through these places, it defines them. But as Earth's climate warms, the deep sea's currents are changing. The melting of polar ice, the alteration of rainfall patterns, and shifts in salinity are beginning to disrupt the very flows that have governed the deep for millennia. Already scientists are observing changes in the strength and direction of the Atlantic meridional overturning circulation, a key part of the global conveyor. If these trends continue, the consequences could be profound, not only for the deep sea but for the planet as a whole. A weakening of thermohaline circulation could mean less oxygen reaching the deep. It could slow the delivery of nutrients, alter larval dispersal routes, and collapse fragile communities that depend on consistency. In the delicate dance of the abyss, even a small change in current can ripple outward, touching every level of life. In addition, human activities such as deep-sea mining and trawling physically disturb current pattern. A mining operation, for instance, might create sediment plumes that disrupt flow, bury filter feeders, or block chemical cues. We are only beginning to understand these impacts, but the message is clear. The pulse of the deep, once so steady, is becoming vulnerable to the heartbeat of the surface world, and yet the ocean continues to move. It breathes, it circulates, and in doing so, it sustains. There is something poetic in that, something ancient and beautiful. These invisible rivers flow through darkness, unseen but essential. They guide fish and coral and jellyfish alike. They speak a language written in motion, one that predates us, and will likely outlast. In the stillness of the abyss, if one listens closely enough, they might hear that language, the soft sigh of a contour current brushing over sand, the rising hiss of upwelling water stirring life from slumber, the long, low hum of a tide passing through a trench. These are not sounds in the human sense, but they are the music of the deep. As we drift here, in the quiet depths, it becomes clear that currents are not merely oceanographic facts, they are lifelines, architects, messengers. They sculpt the world beneath the waves with patience and power, laying the foundation upon which life builds its most intricate forms. The ocean has no heart, but it has a pulse. It has no lungs, but it breathes. And in every gentle sway of water, in every unseen surge of movement, it tells a story of connection, endurance, and life rising from silence. Let us follow that pulse into the next mystery it carries. There are giants in the deep, not the kind that walk on land or loom on horizon lines, but those that drift, slither, pulse, and prowl in darkness, deeper than imagination. They move slowly, quietly. They are older than myth, stranger than fiction, and larger than most things we think belong in nature. The deep sea hides them well, not out of malice, but design, for where pressure crushes, sunlight dies, and the cold chews through steel, these hidden giants reign. The colossal squid is perhaps the most legendary of all. Its eyes are the largest in the animal kingdom, glassy black orbs, the size of dinner plates, designed not for light but for ghosts of light, for the faint glimmer of bioluminescent flashes, hundreds of meters away. It has tentacles longer than a car, armed not only with suckers, but with rotating razor-lined hooks, and yet we know almost nothing about it. Dead ones wash up sometimes. Others are torn apart in the bellies of sperm whales. But a healthy wild adult colossal squid has never been filmed in its natural habitat. It is real, and yet it remains a phantom. Its smaller but equally enigmatic cousin, the giant squid, haunts the mid-waters and lower mesopelagic zone. It grows up to 13 meters long. For centuries it was the subject of sea shanties and sailors' nightmares, its arms supposedly coiled around ship hulls. Today, we know it exists, but even with submersibles and deep-sea cameras, sightings remain rare. It lives in a world without anchors, a drifting, quiet life in an ecosystem built for those who wait. Whales are giants too, though they do not belong solely to the deep. They certainly enter its domain. Sperm whales in particular dive beyond 2,000 meters in search of squid. Their heads are massive sonar chambers. Their clicks among the loudest sounds produced by any animal. These whales hold their breath for over an hour, navigating blind in total blackness, hunting by sound. When they do battle with giant squid, it's an encounter we may never fully witness. Massive beak versus bone-crushing jaw, soft arms wrapped around sleek muscle. The stories are written in scars, but the giants of the deep are not all predators. Some simply exist at scale, oversized compared to their shallow water cousins, inflated by the strange rules of life in the abyss. The giant isopod is one such creature. Imagine a roly-poly bug but half a meter long, with armored plates and rigid antennae. It scuttles across the seabed in slow motion, scavenging for whatever the ocean drops. Whale fool, dead fish, the occasional discarded bait. Its metabolism is glacial. It can go months without eating. It doesn't need to move fast. Nothing does down there. Then there are the jellyfish, ghostly umbrellas floating in near-zero gravity. Deep-sea species can reach massive sizes, with bells over a meter wide and tentacles trailing for meters behind them like forgotten silk. Some glow, some flash, some drift for weeks through silent corridors of salt water. Neither predator nor prey, just presence. One such species, Stygiomedisa gantea, has been seen only a handful of times, but when it appears on camera, it glides with a grace that seems to defy biology. The giant amphipods are equally strange. These shrimp-like scavengers grow to the size of a soda can, far larger than their shallow water relatives. Their translucent bodies and oversized eyes make them look alien, but they are essential cleanup crews of the deep. Like janitors of the abyss, they devour decay and turn it into energy once more. Some giants are armored, others soft. Some glow, some shimmer, others look like shadows made flesh. Consider the deep-sea sea cucumber, which can inflate its gelatinous body into bloated drifting blimps, or the giant polychaete worms, coiled like ancient scrolls across rocks, fringed with iridescent bristles that shimmer under artificial light. These animals live quietly. Their lives stretch long and slow. Some might live a century without ever seeing another of their kind. And then there are the giant sea spiders. Not true spiders but arachnids in form. They walk delicately along the seabed with legs over half a meter long. Their bodies are so small compared to their limbs that much of their internal organs have spilled into their legs. They feed on slow-growing coral and sponges, and their movements resemble puppets suspended in syrup. But perhaps the most haunting of the hidden giants are those we've yet to name. Every year, researchers discover new species in the deep, some big, some colossal, some glimpsed only once. A strange silhouette passes a camera lens. A sonar ping reflects something massive. A trawl net returns with shredded pieces of something unidentifiable. These are not mere fish or cephalopods. These are in the Hadal Zone, the deepest part of the ocean, stretching from 6,000 to nearly 11,000 meters. Creatures exist under pressure, so intense that a human body would be crushed instantly, and yet giant amphipods, snailfish and abyssal eels live and thrive. These animals do not resist the pressure, they embrace it. Their cellular structures are fluid. Their enzymes function best under compression. They are built for silence and shadow. One of the most dramatic finds in recent decades was the giant siphonophore, a colonial organism that resembles a jellyfish, but is actually a collection of specialized individuals called zooids. Some specimens have been measured at over 45 meters in length, longer than a blue whale, and yet they are almost entirely invisible in the water column. Their threads thinner than fishing line, pulsing with faint bioluminescent lights. What unites these giants is not just their size, but the way they reflect life's ability to adapt. In the deep, size is not vanity, it is survival. Larger bodies can store more energy, they can travel farther, they can last longer between meals, they are more efficient in the cold, they can grow slowly, mate rarely and die without being eaten. It's not that the deep prefers giants, it's that it requires. Their growth is slow, often taking decades. Their reproduction is sparse. Some may spawn only once in a lifetime. They are vulnerable to changes in temperature, acidity, noise and sediment, and they are vulnerable to us. Deep-sea trawling can destroy entire communities in a single drag. Mining the seafloor for metals may obliterate species we haven't even named yet. These giants are not just biological curiosities. They are guardians of the carbon cycle, of nutrient loops, of evolutionary history. They hold secrets we cannot yet comprehend. Strange proteins that resist pressure, bioluminescent compounds that might help fight disease, metabolic slowdowns that rival suspended animation. They are not just animals, they are blueprints of resilience, and yet most have never been seen alive. They live where no sunlight has ever reached, where color ceases to have meaning, where direction becomes meaningless. They live in 3 dimensions, floating or crawling or pulsing in a gravity softened by water. Their world is defined by pressure gradients, sound waves, chemical trails and magnetic anomalies. To us they seem alien. To them we are nothing more than a brief vibration in the distance, a sonar click too high to register, a current disturbed by propellers, a flicker of artificial light, then gone. Still we search for them, not only because they are wondrous, but because they matter. They are part of Earth's puzzle. They tell us what life can be when stripped of warmth and ease. They show us what adaptation looks like when time is allowed to stretch into millions of years. And the deeper we go, the larger the mysteries become. In the far corners of the Hadal trenches, we still don't know what waits. Could there be species larger than anything we've seen, living off thermal gradients or chemical reactions in complete darkness? The answer is almost certainly yes. The hidden giants of the deep sea are not relics. They are not leftovers. They are not mistakes. They are proof that Earth still holds wonders we have not yet earned, that discovery is not over, that the unknown still whispers from below. And if you could float there beside them, not in a metal submersible but as something native, slow and cold-blooded and ancient, you would hear nothing. No bubbles, no waves, just the long quiet rhythm of mass moving through darkness, the flicker of a siphonophore's light, the slow drift of a jellyfish's bell, the curve of a tentacle in silhouette. The deep is not dead, it is simply quiet, and full of giants. Let us continue. In a world where light does not reach, the language of the deep is sound. Not the sound of crashing waves or the chatter of gulls, not the roar of wind or the hum of engines. This is a language older than the sunlit surface, a language without words, without voices, without breath. The deep sea speaks in pulses and pressure, in vibrations and rhythms. It speaks in silence so profound it becomes music. Down here, where sunlight dies and vision fails, sound becomes everything. It travels faster and farther underwater than in air. Where the eye cannot see, the ear, or rather the body, listens. Every movement, every heartbeat, every shift in current, sends out ripples of information. In the abyss, to hear is to know, to feel is to survive. The sea itself is never still. Even in its quietest corners, there is always movement. Currents whisper across the seafloor. Tiny creatures flap and drift. Particles fall like snow. And amidst it all, deep sea life has learned to listen and to speak. Sperm whales communicate in clicks, dense bursts of sound that can travel tens of kilometers. These clicks are not just echolocation tools. They are identity markers, tribal codes and perhaps something more. Some researchers believe they function as dialects, cultural signatures passed from mother to calf, generation to generation, each family line with its own rhythm, its own song. These sounds echo through the twilight zone, bouncing off cliffs and canyons, creating sonic maps that only the whales can read. When a sperm whale hunts, it sends out a series of clicks that increase in pace as it nears its prey, a rising tempo that tells a silent story. And when they gather, sometimes in tight circles, heads together and tails fanned out, they click not to hunt but to converse. Long strings of patterned clicks, known as coders, ripple through the water, like Morse code from another world. In other corners of the deep, fish speak in hums and pulses. The plain fin midshipman, a squat little fish with bioluminescent spots along its sides, produces a low-frequency hum by vibrating its swim bladder. Males drone for hours in hopes of attracting a mate. Their sound is steady and haunting, more vibration than tone, a lonely beacon in the dark. Snapping shrimp, usually small, shallow water creatures, have distant relatives in the deep. When they snap their claw shut, it creates a cavitation bubble that collapses with a crack louder than a gunshot. The sound is brief, but powerful. In large numbers, snapping shrimp create an underwater chorus so loud it can drown out sonar. In the deep, these cracks are fewer, but still meaningful, startling warnings, acoustic boundaries, or perhaps just a flash of presence. Even creatures without vocal cords can communicate. Cephalopods like squids and cuttlefish use movement and gesture. They ripple their bodies, flash lights, change colors, and wave limbs. Though the deep-sea species often live in permanent night, many still possess bioluminescent capabilities. They speak through flashes, a sudden burst of blue, a fading pulse of green, a spiral of cold light in total darkness. These bioluminescent displays are often misunderstood as purely defensive. But in the dark, where every flicker stands out like a shout, light can be language. A pattern of flashes may indicate readiness to mate, territorial claim, or even mimicry. Some squid, like the firefly squid, possess complex photophores capable of blinking in deliberate sequences. In the pitch black of 1,000 meters down, that is more than display, it is conversation. But not all communication is intended. In the deep sea, just surviving produces sound. When a jellyfish pulses, it moves water. When a crustacean snaps a limb or scurries across a shell, it echoes. When a fish adjusts its buoyancy, it shifts water. These incidental sounds become part of the deep's ambient language, a background hum of life, like static on a cosmic radio. To many deep-sea creatures, this ambient soundscape is as familiar as the air we breathe. They don't just hear it, they feel it. Some fish detect vibrations through their lateral lines, sensing the movement of water across their skin. Others use specialized pressure-sensitive cells to hear with their bodies. The barrel-eye fish, with its transparent head and sensitive upward-facing eyes, also detects motion through fluid canals, allowing it to sense unseen predators or prey above. Sharks, including deep-dwelling species like the frilled shark, use their ampullae of Lorenzini gel-filled pores on their snouts to detect the bioelectric fields of living things. But these same systems are attuned to low-frequency sounds and pressure waves. A struggling fish, even hundreds of meters away, may unknowingly send out a death knell across the water. This sensitivity creates a world of constant awareness. Every movement is a signal. Every stillness is a message. Silence in the deep isn't the absence of sound, it's the presence of choice. When a creature stops moving, it is speaking in stillness. I am hidden, I am waiting, I am not prey. Hydrothermal vents, some of the most dynamic environments on the planet, hum with thermal energy. The superheated water, bursting from fissures in the seafloor, creates vibrations and noise. Some vents crackle and hiss, others rumble with deep, throaty resonance. Around these chimneys, entire ecosystems cluster: tube worms, vent shrimp, clams and bacteria, all surviving not on sunlight, but on chemistry and the silent signals of temperature and current. The vents themselves become landmarks, auditory beacons in a world without light. Creatures may use their sound signatures to find new homes, detect changes in chemical output, or coordinate spawning events. In the absence of sight, the rhythm of a vent may become the rhythm of survival. Even more astonishing is the possibility that deep-sea animals use long-range, low-frequency sound for migration or navigation. The blue whale's infrasonic calls can travel across entire ocean basins. Eels, which migrate thousands of kilometers to spawn, use these deep hums as guides. Do larval fish rising from the abyss use the sound of reefs or distant currents to find their way? These questions remain largely unanswered, but the deep, as always, holds clues. Scientists are beginning to map the soundscape of the ocean, creating acoustic atlases that track everything from the songs of whales to the grumbles of earthquakes. In doing so, they've discovered that the deep sea has its own unique voice, a layered, polyphonic world of natural noise. But it is not a quiet world. Human activity has invaded even these depths. The thrum of shipping lanes, the seismic bangs of oil exploration, the distant roar of deep-sea mining, all now echo in places that for millions of years knew only the songs of nature. For animals that rely on vibration, on nuance, on silence to survive, this is more than a nuisance, it is a threat. Some fish have stopped spawning in noisy zones. Some whales change their calls to be heard over ship traffic. In the deep, where sound is life, pollution is not always visible. Sometimes it hums. Still, the deep persists. Its symphony continues undeterred in places still untouched. It is composed of more than animal call. It includes the groan of tectonic plates, the distant crash of underwater landslides, the grinding of icebergs over the seafloor and the slow boil of subsea volcanoes. The earth itself speaks here. The planet's bones shift and creak, and the sea listens. For the creatures that dwell in these realms, communication is not a luxury. It is not optional. It is everything. To send a message in the deep is to risk being heard, to risk being eaten. And yet, life speaks. Because without it, there is no connection. Without it, there is only dark. In a world where light cannot penetrate, sound becomes intimacy. It becomes warning. It becomes memory. It becomes the bridge between life and loss. Imagine, for a moment, floating there in the dark, in the stillness. All around you unseen creatures pulse with quiet energy. Somewhere to your left, a whale clicks, searching. Somewhere below, a squid flashes its silent light. Tiny fish hum. Currents whisper against rocks. The world is not silent. It is sacred, and the symphony never ends. It doesn't crescendo. It doesn't reach a chorus. It simply plays, a never-ending, ever-changing composition, performed by billions of unknowing musicians. Every creature, every particle, every current, is part of the score. This is not the loud music of chaos. It is the soft rhythm of balance. A harmony built, not on sound but on sensing. A language beyond language. And even though we cannot hear it with our ears, we can now begin to translate it, with instruments, with understanding, with awe. The deep sea reminds us that sound is not just noise. It is signal. It is connection. It is the language of life in the absence of light. And in the stillness, it's in the deep, where sunlight never reaches and the pressure mounts like invisible stone. Life does not merely survive. It builds, shapes, transforms. The abyss is not just a passive void where creatures drift in isolation. It is a living world, sculpted by the hands of those who call it home. The architects of darkness are not seen, but their work endures, etched into rock, anchored into silt, written into the chemistry of the sea. There is a myth that life in the deep is sparse, fragile, dictated by random chance and drifting detritus. But this is not a graveyard, it is a workshop. Every species that survives here does so with purpose. Some move the earth, some alter the currents, some build cities from coral and colonies from light. They are not just residents of the deep. They are engineers, designers, caretakers, and their blueprints are biological. Begin with the coral reefs of the deep, cold water corals that grow not in warmth and light, but in freezing, pitch-black silence. These coral colonies can rise dozens of meters from the seafloor, forming labyrinthine structures that sprawl across ridges, escarpments, and continental slopes. The most famous, Lophelia pertusa, is a reef-building coral that does not photosynthesize. It catches food drifting through the current, trapping particles with tentacles, building its skeleton slowly from calcium carbonate. Over centuries, these corals create vast underwater cathedrals, intricate frameworks of stone and life. Within these walls, hundreds of other species find shelter. Brittle stars curl in crevices. Squat lobsters cling to the edges. Deep-sea fish weave between the branches. Even after the coral dies, its structure remains, a legacy of architecture that continues to provide for generations. Then there are the sponges. In the shallows, sponges are soft and colorful. In the deep, they become monumental. Some species grow over 2 meters wide and can live for thousands of years. They filter water constantly, pumping vast quantities through their porous bodies, removing bacteria, recycling nutrients, and purifying the surrounding ecosystem. They are not just filters, they are foundation stones. Around sponge grounds, biodiversity flourishes. They provide anchorage, food, and space in a world where space is rare. And yet, not all architects in the deep are builders. Some are sculptors. The burrowing worms of the abyss tunnel through sediments, aerating the seafloor. Their movements churn and mix the upper layers of the benthos, redistributing organic matter, oxygen, and minerals. These seemingly minor motions define the chemistry of the sediment, creating microhabitats for bacteria and microscopic life. Others, like sea cucumbers, crawl across the plains in slow processions, ingesting sediment and leaving it behind, cleaned and enriched. These animals are ecosystem recyclers. Their digestion unlocks nutrients trapped in detritus, making them available again to bacteria and other small organisms. They plow the seafloor with their bodies, turning lifeless muck into fertile soil. At hydrothermal vents, the architects wield chemicals instead of stone. Here, where mineral-rich water pours from the crust of the earth, life does not rely on sunlight, but on chemosynthesis. Tube worms, vent mussels, and shrimp cluster around the chimneys, structures built from minerals that precipitate from superheated vent fluid. These organisms do not build the vents, but they colonize them so densely that they alter their flow, divert currents, and even influence which minerals accumulate where. The giant tube worms, Riftia pachyptela, anchor themselves in the mineral crust, growing over 2 meters tall. Inside, they host symbiotic bacteria that convert hydrogen sulfide into energy. These worms form dense colonies, wrapping around each other in knots of red-tipped bodies, creating layered cities around the vent. When the flow changes or the vent dies, the community collapses, but until then it is one of the most productive ecosystems on the planet. In the cold seeps, similar architecture emerges. Methane seeps up from cracks in the seafloor, and clams and mussels thrive on it, feeding bacteria that live in their tissue. These mollusks grow in thick beds, changing the flow of chemicals through the sediment, stabilizing the mud, and attracting predators and scavengers. Over time, carbonate rock can form, hardening the seabed and allowing corals to take root. A single seep can create a cascading series of changes: chemical, geological, ecological. The architects here are not just the animals, but their symbioses. Life that makes life. Even the simplest creatures have impact. Deep-sea fish often school in mid-water, where their massed bodies form migratory clouds that rise and fall with the day. This vertical migration moves not only biomass but nutrients and carbon. As they feed at the surface and excrete at depth, they drive the ocean's biological pump, transferring carbon from the atmosphere to the abyss. They shape the chemistry of the entire ocean, silently with every beat of their fin. Some species, like certain amphipods, cluster in groups, so dense that they blanket whale falls, the remains of dead whales that collapse onto the seabed. These scavengers strip flesh, redistribute bone, feed bacteria that in turn support other animals. The carcass becomes a community and eventually a reef. Ozodax worms, known as zombie worms, bore into bone, secreting acid, drawing nutrients, and forming coral-like colonies in the marrow. A whale fall may feed the seafloor for decades, and in doing so, it becomes a monument, a garden of bones, grown from decay. Elsewhere, the sea spiders, brittle stars, and crinoids carpet rocky outcrops in slow, waving mats. Their collective movement stirs the water, catches particles, and defines the rhythm of the local current. They become habitat as much as inhabitant. The architecture is not always fixed. Sometimes it flows. Even predators leave behind blueprints. When a deep-sea octopus broods her eggs, guarding them for years without feeding, she often chooses a specific spot, a warm vent, a sheltered crevice, a rock in just the right flow. These locations become hatching grounds, reused by others. Over generations, these sites gain ecological importance, their chemistry subtly changed by the presence of so much life. In the Hadal trenches, where pressure distorts even the shape of water, some of the simplest architects dwell. Snailfish, pale, gelatinous and fragile, lay their eggs in tight clusters on rocks or even inside the gill chambers of crabs. These nurseries alter the behavior of scavengers and change the microbial community in the area. Even here at 11,000 meters, life is making space for life. But not all construction is visible. Many deep-sea animals engineer with chemicals. Bacteria alter their environments at a molecular level, changing pH, reducing metals, oxidizing sulfur. Some bacteria form mats over sediments, visible only when disturbed. Others create entire ecosystems within the tissues of their hosts, bioengineering from within. These microbial architects are among the most powerful forces in the ocean, yet they are invisible to the eye. And in all of this, the coral reefs, the sponge grounds, the worm burrows, the vent gardens, the whale falls, the bacterial clouds, there is pattern, not chaos, not randomness, pattern, intention etched into evolution, strategy written in survival. These creatures are not simply making do with their surroundings, they are reshaping them, improving them, leaving legacies. And when their constructions collapse, when a coral dies, a sponge breaks, a vent shuts down, it becomes substrate for something new. The cycle continues. Architecture into ruin, ruin into foundation, foundation into flourishing, and we are only beginning to understand it. For decades the deep was seen as barren, unchanging, too vast to influence. But now, as we map its features and study its inhabitants, we find networks of impact, trails of influence, communities of balance. Life is not waiting here, it is building, in secret, in silence. There are consequences too. When deep-sea mining scrapes the bottom, it doesn't just remove ore, it destroys architecture, it grinds coral reefs into dust, scatters sponge beds, buries worm tunnels, releases trapped carbon, and fractures communities that took centuries to form. When trawlers drag nets across the deep, they rip through homes, not just habitat. They erase designs that evolved over millennia. Every trench, every ridge, every slope in the deep contains monuments not built by human hands, but by ancient will. Cities without roads, cathedrals without windows, colonies without flags, but they function, they endure, they matter. These architects of darkness do not build with plans, they build with survival, with chemistry, with shape and shadow. Their structures do not rise toward the sky, but sink into the abyss. And yet they are no less grand. The deep is not still, it is under construction. It is the greatest design project on Earth, and its builders do not need to see to understand what must be done. Let us go further. Pressure is the unseen tyrant of the deep. It doesn't shout or surge. It doesn't announce itself with storms or waves. It is quiet, invisible, but absolute. Every meter deeper into the ocean adds weight, not just metaphorically, but physically. Every 10 meters below the surface, the pressure increases by 1 atmosphere. At 1,000 meters, it's 100 times what we feel at sea level. At 6,000 meters, it's crushing. At the bottom of the Mariana Trench, 11,000 meters down, it reaches over 1,100 atmospheres. That's 8 tons pressing down on every square inch. More than 1,000 elephants standing on your chest. And yet, life survives there. Thrives even. So how? This is the mystery of the deep. How fragile things, gelatinous fish, soft-bodied worms, single-celled microbes, can exist under forces that would pulverize a submarine. This isn't just survival, it's mastery. But before we understand how they endure, we must first understand what pressure does. Pressure changes everything. It warps metal. It collapses lungs. It crushes empty spaces. Gas shrinks. Molecules behave differently. Chemical reactions slow. Proteins unfold, DNA struggles to replicate, membranes stiffen. Water itself becomes strange under pressure. It becomes denser, its molecules pressed tighter together, changing how it moves, how it freezes, how it conducts heat. In the deep sea, nothing behaves like it does near the surface. A human at 1,000 meters without protection would not be crushed instantly. That's a myth, but they would die quickly. Nitrogen narcosis, oxygen toxicity, and sheer cold would end consciousness in minutes. At 3,000 meters, every gas in our body would behave unpredictably. At 6,000, bone and blood are no longer reliable materials. By 10,000 meters, even the sturdiest submersibles strain to hold their shape. Yet down here, snailfish drift gently through the trenches, crustaceans crawl, hunt, and reproduce. Microbes live in such pressure all their lives, never rising higher than their trench. What protects them? The answer lies in adaptation, evolution shaped not by light or competition, but by physics. Deep-sea creatures are not stronger than pressure. They are built around it. They do not resist the force. They absorb it. Start with their bodies. Many deep-sea species have no gas spaces inside them, no lungs, no swim bladders, no air pockets, nothing to compress. Their organs are fluid, their tissues soft. This eliminates the risk of implosion. Without rigid structures, there is nothing for pressure to collapse. They are gelatinous for a reason. The famous Hadday snailfish, found deeper than any other known vertebrate, looks like a translucent ghost. It has no scales, no heavy bones. Its skull is reduced to a pliable frame. Its muscles are loose and watery. Its cells are filled with special proteins, osmolytes, that prevent the pressure from crushing their internal machinery. These include trimethylamine N-oxide, or TMAO, a compound that helps stabilize proteins under pressure. The deeper the fish lives, the more TMAO it has. But even this has limits. At a certain point, too much TMAO becomes toxic. This is why there's likely a depth beyond which no vertebrate can live. Not because they're crushed, but because chemistry breaks down. Invertebrates, however, go even deeper. Amphipods have been collected from the Challenger Deep, at nearly 11,000 meters. Their shells are not calcium-based, like shallow crabs or lobsters, but built from aluminum compounds they extract from the sediment, a natural armor that resists dissolution in the acidic Hadday waters. Microbes go further still. At hydrothermal vents and in subduction zones, pisophiles, pressure-loving bacteria live and reproduce in conditions so extreme they would sterilize most life. Their membranes are rich in unsaturated fatty acids, which stay fluid even under intense pressure. Their enzymes are pressure-tuned, designed not just to tolerate compression, but to require it. Some of these organisms cannot survive at surface pressure. For them, the deep is not an obstacle, it's home. Even their DNA functions differently. In pisophiles, DNA repair systems are enhanced, transcription is pressure-optimized, and replication occurs with precision even when compression might otherwise unravel the helix. Their entire molecular biology is built not in spite of pressure, but because of. Pressure also changes how life moves. In the abyss, speed is rare, quick motion demands muscle mass, and bulk resists pressure poorly. Instead, many animals drift, glide, or pulse. The vampire squid moves not with force, but with elegance, fins undulating in slow waves, tentacles trailing. It wastes no energy fighting the medium. Pressure does not welcome struggle. Instead, movement becomes an art of patience. Predators strike quickly, but only once. Prey escape not with bursts but with cleverness. Ink clouds, bioluminescent flashes, sudden stillness. In a world where pressure crushes waste, survival favors efficiency. But pressure does more than shape biology. It shapes the entire ecosystem. At depth, energy is scarce. Food falls from above slowly, unpredictably. Carcasses, fecal pellets, marine snow. In such scarcity, every advantage matters, and pressure influences what can be digested, what can be metabolized, even how nutrients flow through a creature's body. Some species, like the deep-sea holothurians, sea cucumbers, process enormous amounts of sediment, extracting the tiniest bits of organic matter. Others, like vent tube worms, skip digestion altogether, relying entirely on symbiotic bacteria inside their bodies to convert chemicals into energy. Even respiration is altered. Hemoglobins in deep-sea animals often bind oxygen more tightly, extracting it from water where others would find none. Gills are oversized. Blood volumes are high. Everything is tuned for maximum extraction, maximum endurance. But pressure doesn't only define life, it challenges exploration. For scientists, reaching the deep is a feat of engineering. Cameras must be built to survive tons of force. Housings must be vacuum sealed, reinforced with titanium. Lights must function in cold, high-pressure rovers and submersibles that explore the Hadday zone face design constraints unknown elsewhere. A single leak, a single crack, and the pressure does the rest. It is not forgiving. James Cameron's 2012 dive to the Mariana Trench required a specially built submersible, the Deep Sea Challenger, designed to survive 1100 atmospheres. Even then, he could stay at the bottom for only a short time. The descent alone took over 2 hours. Every bolt, every panel, every sensor had to be tested against the crushing grip of the trench. We can't yet stay long in these depths. Not physically, but life does. Life is not a visitor, it is a resident, a native speaker of pressure's silent language. And the more we learn, the more we discover that pressure is not merely something to endure, it is something life has integrated, woven into its structure, its chemistry, its rhythm. The lesson is profound. The forces we fear most can become frameworks. What crushes some, refines others. In the deep, pressure is not the enemy, it is the architect. The maps are still wrong. Even in an age of satellites, AI and rovers on Mars, the deep sea remains mostly unmapped, misunderstood, and unseen. Over 70% of our planet is covered by ocean, and yet we've explored less than 5% of its depths. The seabed, with its mountains taller than Everest and trenches deeper than the sky is high, is more alien to us than the surface of the moon. The final frontier is not out there in the stars, it is here, beneath the waves, beneath the reach of sunlight, beneath everything we think we know. For centuries, we imagined the deep ocean as lifeless, too dark, too cold, too crushing. But every expedition peels back the curtain of ignorance, and what we find is staggering. Living cities around volcanic vents, coral forests in blackness, creatures with no eyes and too many teeth, ecosystems built on sulfur, methane, metal, and still we know so little. The deep sea remains the largest reservoir of biodiversity on Earth, but how many species have we named? A fraction. How many medicines lie hidden in its microbes? How many new enzymes, materials, survival strategies? Every new expedition uncovers organisms with adaptations never seen before. Bioluminescent communication codes, pressure-proof proteins, symbiotic systems so delicate they collapse when brought to the surface. The deep doesn't just house biology, it holds secrets of geology, chemistry, and planetary history. At the bottom of the sea, tectonic plates meet, crash, and pull apart. The mid-Atlantic ridge stretches for over 10,000 miles, a wound in the crust of the Earth that bleeds heat and minerals. Hydrothermal vents pour out metallic solutions, reshaping the ocean floor and feeding life with raw chemistry. Cold seeps ooze methane. Subduction zones recycle the crust. The seabed is not flat, it is alive, rising and falling, cracking and healing, telling stories that no other part of the planet can. The sediments down there are libraries. They accumulate the fallout of ages, ash from volcanoes, soot from fires, chemicals from industry, shells from microscopic life. They layer the history of Earth in millimeters. By drilling into them, we read the climate of 1 million years ago. We see the extinction events, the warming spikes, the cooling valleys, the pulses of oxygen and carbon. The sediment remembers what we forgot. And then there is the role the deep sea plays in Earth's present, not just its past. It regulates temperature, stores carbon, generates oxygen, balances weather. The ocean doesn't just reflect the climate, it shapes, and the deep ocean in particular, moves heat, and carbon around the globe through currents that take centuries to complete a single loop. It is not just a passive sink, it is the circulatory system of the planet. If we understood the deep, we'd understand the Earth. But access is hard. The deep resists intrusion. It is cold, often near freezing. It is dark, utterly black, beyond what human eyes can tolerate. The pressure is crushing, more than 1,000 atmospheres in the trenches. Communication is slow, radio waves fail, sonar blurred. Submersibles are expensive, fragile, rare, and so we look in slivers, snapshots. A few hours at the bottom of the Mariana Trench, a few days at a vent field, a few centimeters of core sample. We extrapolate from fragments, build models from glimpses, and what we miss is everything else. Because the deep doesn't operate on human time, a coral reef in the abyss may take centuries to grow, a sponge might live for 10,000 years, a whale fall might nourish an ecosystem for half a century. Currents move nutrients that were once sunlight in the days of Genghis Khan. When we disturb the deep through mining, drilling, dumping or warming, we disturb something ancient, something that heals slowly if at all, and yet we are accelerating that disturbance. Deep-sea mining, once a fantasy, is now an emerging industry. Companies are testing machines that scrape manganese nodules off the seabed, nodules that took millions of years to form. Others drill into vent fields for rare earth elements. But these ecosystems are not renewable, not on any human scale. A coral reef destroyed at 3,000 meters does not grow back in a generation. It may never return. Noise pollution also penetrates the depths. Sonar blasts, drilling echoes, shipping traffic. Animals that use sound to communicate, hunt or navigate are thrown into confusion. Squid beach themselves. Whales change routes. The deep is not silent anymore, and above all is the threat of warming. As surface temperatures rise, heat slowly creeps into the deep, not as fast, not as visibly, but inevitably. This warmth stratifies the water, weakening circulation, reducing oxygen, stressing life that evolved in near-constant cold. Species move higher in the water column, seeking refuge, but for those already at the bottom, there is nowhere to go. We are changing the deep without understanding it. That is the danger, but it is also the reason we must press forward, because the deep sea is not just a curiosity, it is a necessity. Already, deep sea enzymes are used in medicine, food and industry. Polymerases from deep microbes help us study DNA. Anti-cancer compounds from sponges show promise in trials. Pressure-resistant materials inspire engineering solutions. Bioluminescent proteins illuminate our cells, our brains, our cancers. What else lies waiting? New forms of life for sure, new genes, new branches on the tree of evolution, perhaps even new insights into life's origin. Some believe life began at hydrothermal vents, where energy, chemistry and time converged in the right conditions. Studying these environments may teach us not only how life began on Earth, but where it might begin elsewhere in Europa's ocean, in Enceladus's cryovolcanoes, on exoplanets far beyond. The deep sea is Earth's alien world, but it is also its heart, and we are just learning how to listen to its pulse. We must do so carefully, intentionally, with humility. The ocean's mysteries are not infinite, but they are vast, and they matter. We must protect its ecosystems, regulate its exploitation, and fund its exploration. Not because it is beautiful, though it is, but because it is vital to our climate, to our food, to our future. Every breath we take contains atoms, once cycled through the sea. Every storm we endure is shaped by its heat. Every year we survive is tempered by its patience. And every question we still ask about life, about time, about the planet might yet be answered down there, in the quiet, in the pressure, in the dark.